Salam, hi. I hope everyone is doing well, inshallah, and also enjoying AI Day so far. We have arrived to the talk session, and for those of you who just joined us, I will talk briefly about AI Day. AI Day is an annual event organized by School of AI Algiers. We do activities related to AI, and today we started with AI debate. The topic was the future of AI in Algeria and how we see it and how it's going. So the participants debated about it. Then we had a series of workshops. More specifically, we had 4 workshops. One concerning deep learning, convolutional neural networks, CNNs, natural language processing, NLP, and reinforcement learning. And for those of you who missed the workshops and maybe you wanted to and couldn't or anything, the sessions were recorded and will be available on YouTube the next couple of days, inshallah. Make sure also to check the channel, YouTube channel that has good AI content. And now we arrived to the talk session. We will have 4 wonderful talks done by amazing speakers who will take from their time and be with us here today. We also want to thank AMIX, which is a non-profit organization that is organizing Algeria AI Challenge, for their countless enthusiasm and help. Before we get into the talks, we will start by Keynote, which is done by Hajar Menzian, founder of School of AI Algiers and also a PhD student in deep learning. Hajar.
Hello, everyone. So I hope you're hearing me. Thank you, Nariman, and thanks for all the participants. I am really proud that we are at the 2nd edition of AI Day. And I hope you took the most of the workshops and you take most of these talks. So last year I did a talk about the state of AI in the decade 2010-2020. And I hoped with this keynote to continue the tradition and do the state of AI in 2020. So I thought it will be easier to do the state of AI in just 1 year. But as I noticed, and this is what amazes us with AI, is that the number of papers and the number of applications is growing from year to year. So in a decade, I could easily pick which one is the best, which one is the breakthrough. But in just 1 year, there are a lot of breakthroughs in so much domains. So I will try. I selected some of them. So I apologize if your favorite applications or your favorite paper won't be discussed in this keynote, but I will gladly discuss it in the comment section. Okay. So let's start by talking about some concepts before we go to the applications, the new applications and new breakthroughs. So what is artificial intelligence? So artificial intelligence is the discipline or the field that makes machines decide by themselves. So either it is an expert system where you say, for example, if the temperature rises above a certain degree, then shut down the system. So this is a machine that takes a decision, and this is under the artificial intelligence. It can be a robot that you create that mimic the walk of a human being, or it can be machine learning. And machine learning are the group of algorithms that learns from experience. So they learn this condition or the patterns that ensemble some of the data from the experience, the previous experiences, or the ground truth. And almost every significant milestone in artificial intelligence in the past years was in computer vision, from computer vision to speech recognition to even machine translation, can be attributed to deep learning. And deep learning is a kind of algorithms that is under machine learning. So we are learning from experience from the previous data. And in deep learning, what we call supervised learning, we train our machine by showing examples instead of programming the conditions. So instead of saying, okay, when the temperature rises above 37 degrees, I would say when the temperature, choose the degree, or find the degree among the previous examples and tell me when to shut down my system. And then these algorithms in deep learning consist of this series of layers with multiple neurons, as you can see here in the picture. And when the output is wrong, we tweak or adjust the parameters of the machine. And with deep learning, we could do so many breakthroughs like autonomous driving cars, robots, playing a game of Go and winning against one of the best players in the world, or maybe even artistic paintings with deep learning. Okay, so now let's go to the heart of our keynote and talk about the applications. Yeah, talk about the applications that amazes me in 2020. So first, in computer vision. So computer vision is it englobes the algorithms that makes the machine see, not just capture the image, but understand the image. One of the applications that really amazes me in 2020 is video completion. So in video completion, what we do is that we remove an object from a video. So we have, like in the first video, a man is walking, and then in the second video, the same scene without the man that is walking. So this was done previously by NVIDIA and other companies in static images, not in videos. And this year, a team came with this solution with deep learning to make the same thing, to remove objects, but from videos and not images. So this is quite impressive. The second thing I want to talk about in computer vision is the use of transformers. So transformers are models that are built traditionally or originally for NLP. So NLP is processing sequential data like text or speech. So we want to learn the language and process the natural language. So this was done by transformers pretty well, especially for translation, for example, from one language to another. But here in computer vision in 2020, we used transformers in computer vision. So we didn't use them for text or speech. We use them for computer vision. This is the new thing. So we use GPT-2, which is a special type of transformers, to autocomplete images in an unsupervised manner. What does it mean? Sorry. So we give the model an image without half of the image or some parts of the image. And we asked the model to complete the images, and it completed them pretty well. So if we give like the model an image of a car, but just half of the car without the back, the GPT-2 model will complete the back and draw it perfectly. Also, we have vision transformers. So vision transformer were the state-of-the-art model in image classification and detection in late December and early January, before meta pseudo labels came in. But vision transformers are only using transformers in their model with zero convolution and achieve state-of-the-art model, which is quite impressive as well, just by adding this patch and position embedding, as you can see here in the image. Okay, I wanted also to discuss one concept, which is AutoML. So I put it just under computer vision because most of the AutoML algorithms are used with computer vision models. So what's AutoML? So first, let's discuss the pipeline of a machine learning application. If you want to create a machine learning application, you'll begin by collecting your data set and then cleaning it, and then do some data pre-processing, which means that you prepare your data for your model. And by preparing your data to the model, you may do some data augmentation, or you may not. And then you choose the architecture and the hyperparameters, which means the number of layers, the type of operation that is executed in each neuron or in each layer, and the hyperparameters, the filter size, the kernels, etc. And then you also choose some training hyperparameters, which means that you need to choose, for example, the learning rate, the optimizers, etc. And then you train the model. At that time, you may notice that your model is not very good and you need to update some of the previous step. So you may want, you may notice that your model, for example, overfits on the data. So you may want to increase the number of data or change some training hyperparameters. So you may tweak some of the previous steps, and then you validate your model and deploy it. So this is the basic pipeline of creating a machine learning application. And then AutoML came in and wants to automate these three components. So the data pre-processing, the selection of the architecture and hyperparameters, and the selection of the training hyperparameters. So we want to do this automatically without the human without the machine learning engineer to tweak them, and then we empirically test each hyperparameter, etc. So we want it to be something automatic and something fast and not error prone also. So this is what AutoML is, and it is it is a pretty exciting field, and it begins like in 2015, around 2015, and we have like a lot of algorithms evolving around it. But in 2020, we had this new algorithms, which is AutoML 0 from Google. And the idea of AutoML 0 is to start from a blank program, a completely empty program, and to give the agent, the reinforcement learning agent, to give it a list of different mathematical operations from NumPy, and to say, okay, create a program that will learn to do this task. And the program will slowly learn for example, the linear model, and then it will learn the SGD, and then it will slowly learn ReLU and some other activation, and then it will learn to normalize the data, which is really exciting. And I'm wondering if it can learn some other operations that we completely not know about and that are powerful in deep learning. Okay. So this was about AutoML and AutoML 0 that were in 2020. And yeah, as I said, most of the AutoML algorithms are produced for computer vision models, but some of them are for NLP also. Yeah, and now we're going to talk about the applications and concepts in natural language processing. So in natural language processing, the year 2020 was under the motto, the bigger, the better. So we have seen GPT-3, or the creation or the release of GPT-3. And in GPT-3, we had like 175 billion parameters, which is really huge. Compared to GPT-2, which has only 1.5 billion parameters, it is really huge. So yeah, it's increased the number of parameters and the model size, but also, so I want to highlight that only training GPT-3 is an achievement in itself. So being able to train such a big model is a big achievement in 2020. But also now that it is trained, we can use it to different and several scenarios. We can use GPT-3 pre-trained without retraining it into different scenarios. And one of the scenarios that really excites me is the translation from one programming language to another. So for example, here we have the translation from Python to Java, as you can see here. So we have like the enumerate, the print, and we have the class created in Java, etc. Okay, one of the downside of GPT-3, we are going to talk about another downside later, but one of the downside is that it's only write like a human, but it cannot yet reason like one. So for example, if you give it if you give it a question, which one is heavier between two objects, it won't really know, because it cannot infer the answer from knowing what is the weight of this object and what is the weight of that object too. So it cannot infer, it cannot reason, but it can write like a human. So this is a general problem in natural language processing models. And yeah, and a lot of work is going into that direction to be able to make models reason and not just write like human. Another interesting fact in natural language processing in 2020 is the conversational AI. So we had a lot of assistants in different types of industries, especially healthcare. And the assistant in healthcare can, for example, remind the patients of an appointment, of their medicine, collect their feedback, help them with their medical insurances, or answer some medical questions as well. Okay. Okay, now I think that is the most exciting applications that we are going to see the most exciting applications here. So here we are combining computer vision and NLP. So the first application is look, read, reason, and answer. So this is a model that when given a picture and a question, it can answer the question based on the image. So for example, in the first image on your left, you can see that we are asking the computer which processor brand is featured on the top left. And you can see in the image that we have like Intel written on the top left of the image. So yeah, this is a pretty interesting application. And okay, one thing you need to know is that it doesn't only contain, the model doesn't only contain deep learning, a deep learning model. It contains several components, and one of them is OCR. So with OCR, we detect all the characters and we know what is written. And with another component, we detect all the features that are extracted from the image, for example, the color, etc., the shapes, etc. So we have multiple components in one model, and one of them is OCR. Another really exciting application is DAL.E. The paper is not released yet, but it is supposed to be released early 2021. But you can see the description in OpenAI website, and you can see some examples too. So what DAL.E does is that it generates images from a wide range of text prompts. So for example, like this like in the image, if you give it the text prompt an armchair in the shape of an avocado, it will give some designs of an armchair with the shape of an avocado. So like this is really weird and this is really exciting. And of course, these images aren't in its training data. So it's completely generates these images from, yeah, it doesn't know these images before. Another application from OpenAI 2 is Clip. So this application matches between the text and the image from a big number of different texts. And yeah, this is captioning or image captioning. Okay. Okay, another field that is living its AI moment now in 2020 is biology. So you may have expected this, and we need to talk about it, but let's discuss it. So we have like the number of publications in PubMed involving AI in biology, either reinforcement learning, computer vision, NLP, or just deep learning, are growing with almost like 25,000 in 2020. You can also check a survey of deep learning for scientific discovery, which is a paper that we read in the reading sessions organized by School of AI Algiers. And yeah, the YouTube recording for that reading session is also available in our YouTube channel, so you can check it too. And it summarizes what deep learning is doing in the scientific discovery field. Of course, the biggest breakthrough in biology is the protein folding solution that DeepMind revealed, or that DeepMind proposed. So the algorithm predicts the shape that a protein will take based on the genome recipe. So this is a pretty hard challenge, and we didn't have a solution to that problem. And now we have it thanks to DeepMind and deep learning and reinforcement learning also. So with AlphaFold. So in biology, why biology is living its AI moment now? Because of two factors. The first factor is the availability of data sets. So we have like rx.ai built an image data set of cells treated with various chemicals, and you have all the different images with all the different chemicals and other new chemicals that are being added each day. And the second factor is the graph neural networks. So graph neural networks are a type of neural networks, a type of deep learning algorithms that are dedicated to graph structures. And you're going to hear more about them in the last talk. Okay. Now, another domain where DeepMind is leading the game also is reinforcement learning. So with their paper mu0, they published a model that is able to play any of these four games and generalize to any of these four games and learn the rules of the game while playing. So this is really incredible, and for many scientists, this is considered by many scientists as the first step to AGI, which is artificial general intelligence. Okay. So yeah, I wanted to add this slide just to compare with last year and what we did last year. We compared between PyTorch and TensorFlow, and yeah, here in this figure, we can clearly see that PyTorch is leading now. But as we said last year, the same conclusion stays, that TensorFlow and PyTorch are converging to the same framework, but with PyTorch having the power of debugging in Python, etc. Another variety of tools that are really being released each day and with so many updates are the compilers. So I encourage you to go and check the keynote of the PyTorch Developers Day, where they are really explaining how they integrate a compiler into PyTorch and why they integrate it and why it makes deep learning more efficient by optimizing each operator of the model. So Papers with Code is not a tool, is not a library, nor a framework, but I wanted to add this website here just as to let you know that this website exists. So in this website, you have like a data set of all the papers with their code. If they have like any implementation, you have it there. And also you have a list of the state of the art in each benchmark. So this is pretty good, and I encourage you to use it if you're interested. Okay, to finish my keynote, I want to talk about some side fields in AI that are really important and that are seeing an increase in the number of papers, especially in 2020. So the first one is efficient deep learning. With efficient deep learning, we aim at, so yeah, if you're like me, you imagine the future filled and populated with tiny little devices that can help us in our daily life. And these tiny little devices have to be empowered with deep learning. And to have deep learning being executed in these tiny little devices, we need the deep learning models to be smaller, to be faster, and to be energy efficient. So this efficient deep learning is the field of all the algorithms that help with that helps achieve that. And this is the content of the first two talks. So be tuned. And then we have like privacy preserving machine learning. So we want to have basically in the in the pipeline of each machine learning application or deep learning application. I have my smartphone, I have my data in it, I take a picture, I send the picture to the cloud execute the model, and then send me back the output of the model. So yeah, sending my image to the cloud and then getting back the result is not really secure. So how can we make this secure? And this is the content of privacy preserving machine learning, which is our third talk. Another side field of AI that won't be discussed in any of the talks is the AI responsibility and fairness. So yeah, if you can see, like here in the picture in this example, we are dealing with the playground of OpenAI, just working with GPT-3. And if I give like the two words to Muslims, and then I let the model GPT-3 complete the sentence, it will write two Muslims, one with an apparent bomb tried to blow up the federal building in Oklahoma, etc., etc. So this is really biased, even if GPT-3 has learned from the biggest corpora available in the internet, with all Wikipedia articles, with all different website articles, etc. So it still have this bias, and it is still biased against one religion or against one race. So we need to avoid this by treating our data, checking our data, and checking our algorithm at the end. So I think I finished. So thank you. I will give back the mic to Nariman.
Thank you very
Thank
much.
you, and enjoy the talks. I hope you enjoy this AI day talk session.
Thank you very much, Hajar. We surely enjoyed your presentation, and also it was cool knowing about all the stuff and all that happened in last year, especially that it was sort of tough year for all of us. So knowing that there are some improvements and some new technologies is surely helpful. Thank you very much for the presentation.
Thank you.
Now we will move to the talks. We'll have, as I said, 4 wonderful talks in different topics. Don't hesitate to leave any questions you have in the comments, and I'll make sure to ask as many of them to our speakers as soon as they finish their talks. So for our first talk today, we are honored to have with us Bougli Hassan Gouti. He got his PhD in France at IMT Atlantic, and now he is a postdoctoral at Mila and works on optimizing and compressing deep learning algorithms. He also works to design hardware architectures that implement efficiently optimized deep learning algorithms on embedded systems, such as FPGAs. Gauthier received 2 Best Thesis Awards after defending his PhD, Association Française pour l'Intelligence Artificielle et Fondation Mines Telecom, and he is one of the ICLR workshop organizers entitled Hardware Aware Efficient Training. Today, he will talk about processing deep learning on chip. So welcome with us, Gauthier, and thank you for accepting our invitation.
So first of all, I would like to thank you for the invitation and for the event you are organizing. And okay, so I think I can share my screen.
Yeah, sure.
Share screen, yes. Here we are. So everyone is seeing my screen.
Yes, we can. Thank you. Yes.
Okay, so I can start. So as you said, so my name is Gauthier. I'm a postdoc at Mila now, and Mila, it's a Montreal Institute for Learning Algorithm. Is a public laboratory at Montreal in Canada, in which we work on deep learning in general, and try to advance the research concerning deep learning. And today I will present you some stuff I've been working on, especially trying to reduce the complexity and the memory usage of the deep learning required during inference, especially trying to apply deep learning algorithms on embedded systems with limited resources, such as smartphones. And so for my presentation, let's just start with a bit of context. So we know that deep learning in the last decades became state-of-the-art in numerous domains, such as computer vision, natural language processing, and even games. However, to be state-of-the-art, deep learning methods require a lot of energy, hundreds of millions of operations, and a large memory, to store the trainable parameters. And also to do deep learning, it's really expensive because we need to buy some expensive devices such as TPUs and the GPUs that cost more than 10,000 euros each sometimes. So, as I said, deep learning is the state of the art in numerous domains, but this really has a big cost. So to avoid and try to reduce that, we put some research on that, because all of this constraint introduce some challenges. So a first one is a technical challenge, in which, as we said, we need a lot of we need to compute a lot of operations, billions and billions of operations, which require time. Which means that using deep learning, usually we need to let's say we need a certain amount of time to compute the output given an input, and then it doesn't goes with the real-time applications. Also, the number of of operations and the parameters we need to store does not goes on limited resources embedded systems. Another challenge is a scientific challenge. So usually large architectures are really hard to see. So when we train a neural network with billions and billions of parameters, the parameters inside the deep learning, their values are changing, but we don't really understand what is happening inside because it's really complex. So if we try to reduce the size of neural network, maybe we can start understanding what is happening inside during training, and having some ideas on how deep learning works. Also, to test an idea if it's good or not, we need to simulate it, because we don't have a mathematical formulation behind. And to simulate an idea, it requires a lot of time, which limits the progress of the field. Finally, a societal challenge would be the energy required to train or test the deep learning methods, and also the accessibility of deep learning. So, as I said before, to train deep learning, or even to do the inference to test the deep learning model, we require the expensive devices. And so not everyone can buy these expensive devices, which limit the accessibility of deep learning to everyone. And here, so we will try to address these challenges. And to do that, in this presentation, we will briefly talk about the deep learning, what is deep learning, and the data sets usually used. Then we will introduce some efficient inference methods, and finish with a conclusion. So a basic introduction or definition of deep learning is just an assembly of functions. And usually we define a function by an entity called layer. And in deep learning, and especially in computer vision, we have two most important layers or functions. So the first one is the fully connected layer. The layer is called fully connected because, as we can see in the picture, we have all the input layers connected to all output layers. The second most important layer is the convolutional layer. So different from the fully connected, since the weight here or the parameters of the deep learning are shared. It means that, for example, we can see here numerous rows in green, which means that the same weight or the same parameter is used numerous times, and also not all the input neurons are connected to all output neurons. So this layer, contrary to full connected, is less complex and reduce the number of parameters required to train or test a deep learning. Now, the usually dataset used in computer vision are, for example, CIFAR10 and CIFAR100. CIFAR10 and CIFAR100 are tiny images, 32 by 32 pixels, and it contains 10 and 100 classes respectively. A class here is a category of images. So for CIFAR10, as we can see in the picture, we have the class of plane, car, bird, cat, etc. Another interesting dataset, it's an ImageNet. So it's a Google dataset in which we have high resolution images. And usually if we want to convince community that our idea works and we get good results, we need to obtain some results using this ImageNet dataset. Now here, what we are trying to see if, for example, we know what is deep learning, we know the dataset, and the question would be, okay, if I have this dataset, which we know that there is a lot of maybe millions of models in deep learning, which one is the best? And the answer to this question is there is no the best solution. It depends on the budget we have. For example, in this picture, we can see in this figure, if we have the budget of 100 megabyte, the best solution would be the SEBN inception. And using this figure, we can draw this curve that may represent the optimal Pareto. The optimal Pareto means that all the points on figures on this curve represent the best trade-off memory accuracy or error. So, for example, here we can easily see that if we we want, or our memory constraint is about 250 megabyte, we better use the SE ResNext instead of VGG here, because they have the same memory, but the error is really huge for VGG comparing to the ResNext. And so this is the models we have, and we will try during this presentation to apply some compression method to reduce the complexity and the memory of the deep neural networks, and see if applying such a method we can have some points below this curve, or if this curve is really the optimal Pareto. So and to do that, we start by presenting what is a quantization. So let's consider we have two layers as a baseline, layer 1 and layer 2, each one having a certain number of parameters or weights. So if we focus on this value, we can consider this value is encoded on 32 bits. The idea here is to use less bits to represent this value, and doing that, so we go from 0.478 to 0.5, which means that we approximate the value using less bits. And doing that, it allows us to reduce the memory because we use less bit to represent a value. But not only reduce the memory, we also reduce the number of parameters, because and reduce especially the complexity, because here, for example, instead of doing a 32 by 32 multiplication, we will compute only an 8-bit by 8-bit multiplications. For example, if we goes from 32-bit values to 8-bit values, and an 8-bit by 8-bit multiplication is less expensive than 32 by 32-bit multiplication. So this method allow us to reduce at the same time the memory footprint and the computational power. Okay, this is great, but the question would be how many bits we can use? Can we just reduce the number of bits, or there is a limit? And to answer this question, we did some simulations or some tests. So here we have some state-of-the-art neural networks trained on Cypher10 as ResNet 18, SynNet, and MobileNet. And what we do on the two figures, we reduce the number of bits for weights and the activations. And we can see that until 8 bits for the two cases, we still achieve almost the same accuracy. So we can reduce the number of bits until 8 bit, and we can see that there is no drop in accuracy. But if we go beyond that, the drop in accuracy is really huge, especially if we go for 5 bits. We see that the accuracy is completely lost. So the drop in accuracy is really big. And so here we just naively reduce the number of bits. We start from a fixed point representation, the 32-bit, and we start reducing the number of bits. But the question would be here, if we don't do that naively, can we continue reducing the number of bits, or the 8-bit is really the limit? And the answer is yes. We can even go to, using only 1 bit. And the most famous method that introduced this is called binary connect. So binary connect use a straight-through principle, which means that we take the weights or the parameters in the deep learning, and we map the values to their sign. So if the values are positive, we replace them by 1. If they are negative, we replace them by -1. Then we compute the feed-forward and back propagation in deep learning. We compute the gradient, and then we use the gradient to update the weights. But we don't update the weights, the signs. We really update the floating point values, so the real values before the map we did with the sign. Another method called binary weight networks has been proposed and outperformed the binary connect just by adding a scaling factor. So instead here, instead of replacing the values by 1 or -1, we replace them by alpha or minus alpha. And alpha here usually represents the mean average value for the parameters for one layer. So we will have different alphas for different layers. And doing that on different state-of-the-art architectures trained on Cypher10, we can see that especially binary weight connect, it achieves a comparable accuracy to the baseline, which is the full precision here for ResNet, DenseNet, and MobileNet, while reducing the number of the memory usage, because we use only 1 bit instead of 32 bits in the full precision. We reduce the complexity. And also here, what we the most interesting thing we did here is that all the multiplications are replaced by just a multiplexer or a condition. For example, if we have a multiplication between an activation and a weight, and we know that the value of the weight is 1 or -1, so the output will be equal to the input or minus input, which means that we can replace the multiplication operation by just a multiplexer or a condition. So in electronics, a multiplexer is really a low-cost devices which allow us to reduce the complexity, and instead of doing multiplication, we can just let's say consider the value of the weight and say, okay, the output will just equal to the input or equal to minus input, so we don't have to compute any multiplication. Now we talk about another compression method which is called pruning. And to do that, we reconsider the same scenario, layer 1 and layer 2, each one containing parameters. So in the pruning, we try to consider the less important weight and prune them. So prune them, it just replace them by 0. And we can see that here we use 2 different structure of pruning. The first one in the layer 1 is non-structured pruning, and layer 2 is structured pruning. So in non-structured pruning, we prune the weights without any structure, and this is not really efficient method because we need to keep in memory the values of the index of the weights that has been pruned, and we still need to compute the operations corresponding to the pruned values. While in structured pruning, all we need to keep in memory is the rows where the pruning has been done, and we can directly discard or avoid the multiplications or the operations corresponding, for example, to the first row and the fourth row. And so it's allow us to reduce the memory and the computational power. So as we said, the pruning evaluates the importance of neurons and eliminates the less important ones. The non-structured pruning is not really exploitable except if we have a large level of sparsity, while structured pruning is really exploitable because we can just eliminate filters, kernels in layers, and then just really reduce the size of the network and reduce the operations. So here we introduce another method based on pruning, and this method try to replace the convolutional layer we present at the beginning by another layer that is less complex. And to do that, we just consider an easy case in which we have a one-dimensional convolution, in which we have our input x, our output y, and a kernel of size s. So here we have numerous kernels, each one having three parameters because it's one-dimensional kernel. So what we do here is we try for each kernel, we identify the most important neuron, and we keep this neuron and prune the others. So as we can see here in the first column, we consider that the first parameter is the most important one. We keep this one and prune the others. We do the same thing for the other columns, which means that at the end, we end up only with one value per kernel. And instead of computing the convolutional operation, we can compute only multiplications. In addition, to make it more efficient, we will try to compute the multiplication corresponding to this value and this value at the same time. And to do that, we can just keep this column as it and move this the second column by 2 steps, which give us this configuration in which we have our shifted input x, our output, and the convolution with kernels is replaced by just multiplications. So the method we introduced here called shift attention layer. So shift because the input is shifted, and attention because we use attention mechanisms to decide which weight is the most important. So this method is really exploitable because it's structured pruning. It reduces the number of operations, and more important, replace the complex convolutional operation by just a multiplication. If we compare this method with other pruning methods, we can see that for Cipher 10 and Cipher 100 on ResNet 20, we achieve a better accuracy while using less number of parameters and computing less number of operations. Now, what we saw so far was a pruning method and the quantization method. If we try to combine between them, so we said that shift attention layer replace the convolution by multiplication, and binary connect and binary weight network replace a multiplication by low-cost multiplexer. So if we combine between them, we can replace the whole complex convolution operation by just a low-cost multiplexer, which means that instead of computing a convolution on the input, all we have to do is saying, okay, the output will equal to the input or minus input. And of course, we need to test that and see how it works. And if we do that on ResNet 20 trained on Cipher 10, we can see, especially when we combine shift attention layer with binary weight network, the the drop if accuracy is not that important. We achieve almost the same accuracy as the baseline while reducing the memory usage. And more important, as we said, we replace the convolution by just one multiplexer. Now we consider another method to reduce the energy consumption, and to do that we can think about it naively. Imagine we have a deep learning running on an embedded system, and what we do, we just reduce the input voltage of the embedded system to reduce the energy. So doing that, we will create some errors inside the memory of the embedded systems, and the what we call here on-chip memory. And usually we store on this on-chip memory the parameters of the deep learning, which means that we will introduce some errors inside the deep learning parameters. But the question would be here is that really important to introduce some such errors, or can the deep learning continue working even when we introduce this kind of errors? And to answer this question, we introduced a model between to have a relation between the probability that a weight is observing a fault, an error, and the energy consumption. And we consider here the energy as the number of parameters plus the number of activations. And we test our methods on some state-of-the-art neural networks trained on cipherchance, such as ResNet, MobileNet. And for our testing, we consider two scenarios. The first one is what we call here reliable implementation, in which we don't reduce the input voltage. We don't introduce any error. All we do is naively reduce the size of the network. So by pruning randomly some parts of the network. The second one is the faulty scenario, in which we don't touch the size of the network. All we do is just reducing the input voltage. And doing that, what we can see is that until a certain point, for example, here for MobileNet, the curve in the green, until a certain point, we better reduce the input voltage than reducing the size of the network. So we continue our experiments with the three different points that will represent a baseline, and these three different points are represent a pre-act ResNet 18 with different sizes. So we just take the pre-act ResNet 18 and we prune randomly some parts of the network to get these three different points. And then from this different point, we start reducing the input voltage. And what we can see here is that we have three different regions, which means that there is no best solution. It depends on what we are targeting. For example, if we are targeting an energy consumption in the region 3, so we better first reduce the size of the network and then reduce the input voltage. If we are targeting an application in the region 1, so we better just reduce the input voltage without touching the size of the neural network. Now let's consider another approach in which we will try playing on the importance of each layer. We know that in deep learning, layers have different size. So if we introduce a different amount of errors on different layers, we can observe, we try to observe if, for example, we gain some energy doing that without increasing the error. So doing that and comparing to our first scenario, in which the same amount of error is introduced on all the layers, we can see here the curve called the default outperforms the others, which means that we better introduce a different amount of errors on different layers. And actually, this not surprising, because if we come back to this figure and introduce an error on the first layer, this error will be propagated through layers and become more important. So we better introduce the error on the last layer to not propagate it and make it more important. Also, if we introduce an error on the last layer, we can see that the last layer has a lot of parameters comparing to the first layer, which means that the parameters that are not where we don't introduce an error can continue working and try to let's say try to make the work of the other parameters. So we try to introduce a large amount of errors on the last layers, and just a small amount of errors on the first layers. Now, what we did so far in this experiment is that we train a neural network, we put it on the embedded system, and then we start introducing the errors. So when we do that, the neural network is not adapted to this kind of errors, so it doesn't know what is happening. And to help him to be more robust against such errors, what we do is trying to introduce the same kind of errors even during training. So we train the neural network with these errors, and if we do that and introduce different amount of errors on different layers, we end up with this purple figure in which we can see that the energy is almost is divided by almost 5, while the accuracy is almost the same as the baseline. So we could really reduce the energy consumption without or with just a small drop in accuracy. So now we saw different methods of compressing neural networks. Let's compare between them, and to do that, we consider two state-of-the-art lightweight networks, such as MobileNet and SqueezeNet, and a third baseline, which is ResNet 18, in which we just reduce the size of the network to having this curve by randomly pruning some parts of the network. And we can see just here with our baselines, so that doing naively and randomly a pruning on ResNet 18, we end up with a better result than MobileNet and SqueezeNet. Now we apply on ResNet 18 binary connect and binary weight network, and we can see that for binary connect, we better just reduce naively the size of neural network. But on the other side, binary connect also reduce the complexity by replacing the multiplication by just a multiplexer. For binary weight network, it's another story, because we can see that binary weight network outperform our baseline. Now we apply a shift attention layer on our network, and we can see that it still outperform the other methods. And finally, we apply a different amount of errors on different layers during training on the network, and we can see that it's almost the same result as shift attention layer. So we can say that shift attention layer achieve and the faulty method achieve a better trade-off in energy accuracy than the baseline. And also, if you remember at the beginning, we said that we will try to get some points under the curve that may represent optimal Pareto. So we can see here that applying some interesting compression method allow us to even go further this curve and achieving better trade-off between accuracy and and the energy. So to conclude, we can say that here we talk about efficient inference. Since implementing deep learning methods on deep neural networks is with unlimited resource device is a real challenge, but we try to use compression method to make it more efficient. And another and a naive idea, as we saw, it just reduces the input voltage of some embedded systems. Now the directions, the things we are working on is that we try to combine, as we sorry, as we saw between pruning and quantization. We try to see which other methods we can combine between them, and also we try to reduce the complexity of training, because all we saw so far is that the method tried to reduce the complexity of inference. we were trying to see if shift attention layer works on other methods or context other than just object classification. And finally, as we saw here, for example, for binary weight, binary connect and binary weight network, we said that we will directly use one bit to represent weight and activations. So we are working on method to see if the network will learn during training how many bits each layer required to represent the values of each layer. Thank you.
Thank you very much for the talk. It was like very interesting. There are a couple of questions, if it's possible. The first one says in binary connect means that we will take all weights as binary. So going from 32 bits to 1 bit wouldn't affect the model results.
So actually, this let's just here, yeah. So it affects results for sure. We can see that here we have a drop in accuracy from 32 bits, for example, to 1 bit for binary connect and binary weight network. You can see from the accuracy is 95%, it goes to 93 or 94%. So we have a drop in accuracy. But the drop in accuracy is not that important, and we can say, okay, we can let's say allow this drop in accuracy, because what we gain in counterpart is really huge. We reduce the memory, and more important, we replace all the multiplications by just a low multiplexer.
Okay. Thank you for your answer. There is also another question, says that the FP16 will reduce the complexity of computing and also the model size.
Can you repeat the question, please?
The FP16 will reduce the complexity of computing and also the model size. I guess he means that it should reduce the complexity of computing, but does it also reduce the model size?
Yeah, so FP16, yeah, for sure, it reduces the number of operations, because, for example, in embedded systems, usually the device responsible for computing the multiplications is called the DSP block. And for example, to compute a 32 by 32 multiplication, we use about 4 DSP blocks. To compute the FP16 multiplications, we use between 2 and 3 DSP blocks. So it reduces the complexity, it reduces the resources we use to compute the multiplication, and it divides the size of the network by 2. But the thing is, here we are trying to go further and continue reducing the complexity and the memory usage. So here, for example, for with binary connect, instead of dividing the size by 2, we will divide it by 32. So it's 32 smaller than the full precision, instead of just 2 times smaller.
Okay, thank you. Thank you for answering. And also, thank you very much for being here with us today and sharing with us. It was really interesting. Appreciate
Thank
that.
you for presentation for the invitation.
It was a pleasure to have you. Thank you. Now, for our second talk, we are honored to have with us Sophia News. At Intel, Sophia leads the software hardware core design for Intel Edge AI platforms, focusing on deep neural network inference, offload, and acceleration, as well as the design of and prototyping of software enablers for HDNN inference. Sophia obtained his engineering and master's degree from Easy Algiers, ex-INI, and PhD from NAR Institute of Science and Technology in Japan. In his talk today, he will share with us about efficient neural network inference on edge AI platforms. And also don't forget to ask him any questions in the comments. I will try to forward them to him as soon as he finishes. So welcome with us, Sofiane, and thank you so much for accepting our invitation.
Thank you very much, Nariman, and thank you for the invitation. Thank you also for Hassan for the great talk. It was very interesting, and I think mine will be complementary. Tell me if you can see my screen.
Yes,
Perfect.
yes, thank you.
Okay, sorry, I have to go back to my first one. Okay. So as you said, as I said, thank you very much for your invitation. It's a pleasure for me to give to be linked with my first university I graduated from in 1997. At the time, it used to be called named INI. Now it's a lot of stuff have changed, but I think still the same level, same enthusiasm, and all of that. It's great to see you guys doing this great job. So yeah, I will be talking about efficient NN inference on edge AI platforms. As I said, it will be complementary somehow to the talk by Hassan. So I will not go through a very deep introduction. I will try to go straight to what I wanted to highlight in this call. Nevertheless, I will start with a brief introduction to why edge AI. Then I will start with talking about how to design application for edge AI. What are the stuff that we need to care about? What are our level of control to leverage or to take into consideration the limited resources and in our design and different levels of the NN tool chain and pipeline. So then there are a lot of stuff that we can talk about because we have different levels of control, but I don't think we can cover all of them. So I will maybe spend some time talking about Tensor Compiler, and then introducing few or at least one advanced feature and how it is being handled and what are the challenges associated with bringing these advanced features, and that will conclude my talk. So as I said, why edge AI? I think we know that there are a lot that has been done when it comes to infrastructure and tools for massive data processing and knowledge discovery. From cloud, edge, on the edge, and everywhere. So a lot of progress was both on the infrastructure side, but also on the processing side. But the fact is that the data growth rate is much higher than what we can cope with. So so the question now is, what can we do? Can we wait until the data become big, or is there anything we can do to try to reduce or to have kind of scalable solutions for dealing with this type of all this massive data streams? So I think the answer will be we need to deal with the full life cycle of data rather than waiting the data to become big. And if we look at the data life cycle, it starts from gathering to farming to mining to understanding, and those are different levels of semantics that will mapped, or to which the data are mapped in their life cycle. So data gathering refers to the data capturing from at sensor level. Farming means the way to represent the data, like dimensionality reduction, description, and all of searchability, and all of that. Data mining is trying to extract some meaningful information from the data and using clustering, classification, pattern recognition, and so on. And then there will be a series of semantic levels that we can map on top of that can range from simple detection to activity recognition to social behavior analysis and so on and so forth. And that has no end to it. So at each level there is something we can do. And when we are designing an application, in general, complex application, especially when it comes to like large scale application, like for example video surveillance and so on. So it's important to try to push the compute to the earliest possible in the life cycle. So if there is anything we can push to the camera to, for example, to detect people, then that's what we should. That's what we can do. We cannot, of course, we cannot do kind of aggregation or tracking in single camera. We need to have like this will go to the gateway or somewhere, and then so depending on what level of semantics, there will be a right place for it that goes from the camera to the cloud or to the center of processing. So today we are talking about edge, and the edge is now the kind of a battlefield for all the big corporations and players. All the I think if we see what the latest development in edge AI and endpoint platforms, I think what we are witnessing is a higher complexity when it comes to hardware design. The newest platforms are features like dedicated accelerators that are very highly complex. Why they are complex? Because they are bringing disruptive features that's to gain more efficiency, and that's the main features that are features are sparsity and low precision. So Hassan was talking about low precision. But also sparsity is something which can be also thought of as a complementary or competing, because they are both a kind of dimensionality reduction techniques. So if you are very sparse, you have maybe a little bit less chance to go to much lower precision and so on and so forth. So there are a lot of work that are trying to find what is the right balance between sparsity and quantization or low precision. And depending on what platform we are talking about, and depending on how the platform leverage one or the other, we may go for one or another. And that's maybe will be covered in when I'll be talking about hardware aware stuff that we can do to leverage this complex feature. So if we are designing an application in general, or let's say deep learning application, the first point is we start with designing a topology, an end topology, and then the next step will be training. And after training, we end up with a model that is ready for deployment. Then so there will be a complex compiler, and that complexity is proportional to the complexity of the hardware. And that Tensor Compiler is the element which is, or the component which is translating the network from its original form to executable form, and then the runtime. So during the inference, there are also the runtime module, which is executing the inference based on the instruction from the Tensor Compiler. So if this is that is the same thing whether you are in a like a data center or edge or cloud or wherever. But what is when we have an edge platform with very limited resources and very complex architecture, then and with advanced features like sparsity and low precision, then there are a lot of stuff that we can do at every single stage to leverage that complexity and those features. So starting from the topology design. So we have this. I mean, recently there are a lot of work in like network architecture search, and that network architecture search can be thought of differently when you are talking about different platforms. For instance, if I have a platform which leverage better depth convolution than for example 2D or 3D convolution, then if I account for that, I can push my architecture search to promote or to enhance or to bias the search towards something that makes sense or that can be leveraged better on my platform. So there are a lot of stuff that can be done at topology level to come up with an architecture which is better fit for our hardware. Another example, for example, if I know that my hardware compute, like the Mac how to say grid size is a kind of has a 16 channel depth. So I know that whatever convolution I have, my DPU or the processing element always produce or compute 16 channels at a time. Then I'm better off producing architecture which has layers with multiple of 16, because if it is less than that, I'll be spending that time anyway. It's better, you're better off, filling the gap rather than wasting the compute cycles. So at training level, also there are a lot that we can do to try to leverage the quantization or low precision and sparsity. So here we have a lot of sparsity aware training techniques and also quantization. I think Hassan was talking, Hassan talk fits exactly here when how to find the lowest precision which gives with acceptable loss of accuracy. And that now if you have a platform that doesn't leverage low precision, then it doesn't make sense to do anything here. You're better off just designing not doing any low precision. So the third control point is the Tensor Compiler, and that is the layer which is in charge of translating that network which has been designed and trained into an executable form. And that's normally we have two parts of in that compiler. So we have a number of optimization passes. Some of them are generic; they are hardware independent. Like for example, when we talk about vertical fusion, horizontal fusion, like for example, if you fusing scale layer with convolution, with the weight of the convolution, and all of those things. So every single platform will benefit from those hardware independent optimization passes, while the hardware dependent optimization passes, those are specific to the platform, and those will take into consideration the specification of the platform. For example, what is the compute hierarchy, what is the memory hierarchy, how the data are going to be split between the different compute elements, and all of that. And that I mean, in general, the Tensor Compiler, if you want to have efficient deployment and efficient inference on a platform which has a complex accelerator, that Tensor Compiler will reflect that complexity. It will be quite complex, and it's hard. And so next, what I'm going to say here is the hardware. This software, this compiler will become a kind of the bottleneck and also the main differentiator between different platforms. So how it is designed in general, everyone thinks about this in different way. So but in general, it is you have some hardware specifications, and you have from where you can we derive a kind of configuration space and also cost models, and those so the configuration space will encode all the potential, all the possible configurations, and the cost model will be used to optimize the global cost. And when I talk about global cost, we are talking about promoting or optimizing the data locality, which means optimizing the compute and the data movement. So if, for example, we take a complex topology like Euro before here, and you can see here, this number of convolutions. So for your information, I think most of the dominant operation in most of networks is convolution, and so that's maybe what most of the platforms try to optimize. So if we have a topology like this one, the Tensor Compiler it will translate it into something like this, where you have on the top you have the data movement like a DMAs, and on the bottom you have the compute. So this compute, each block of compute here is a large number of compute elements which are distributed between the different compute elements in a synchronized way. It's quite complex list of instructions depending on what type of tensor compiler we do. Is it layer level? Is it instruction level? Is it subtensor level? And so on. So this is first the top here. You see it's non-optimal in the sense that you are serializing everything. You move the weight of the first layer. When you finish the movement, you do the compute, and basically what maybe something I didn't describe well here. Usually we have for embedded platforms, you have the DDR and you have the local memory, and so usually the compute element operates on local memory, which is very, very fast memory but very expensive. So for target platforms, it's quite tiny. And that's it makes you cannot just put all your weight once and for all, and then you will be just computing. You have to optimize the usage of this local memory. So as I said, so non-optimal compute schedule on the top, where you can find you move data. Once the data are in the local memory, you start the compute, and then you wait for the second pack of data or second wait for the following operation to be loaded, and then you do and so on and so forth. So basically, you are serializing the compute and data movement from back to back. So a more optimized schedule where you don't have or you have less resource constraint than the extreme case on the bottom. So you try to say, okay, why do I need to wait? If I can fit the data, I can overlap the data movement when I'm doing the compute of the first element, and then when I reach the execution point of the following one, the data are already there. And so that's what you end up with, something like this. You have on top, you have at the start you are more compute bound, at the end you are more data bound, and that's fine. I mean, if you can do this and you have enough resources to do this, this is the best thing to do, and that would be true for servers and so on. But this is not the case for target or embedded platforms and the agile platforms. And the lowest case here is true for those platforms where you cannot fit even a single layer sometimes, and you need to go kind of splitting the same layer into sub layers, and you do kind of so for example here, when you are compute bound, compute bound means you are dealing with small weight and big tensors. Then you instead of spinning the data back to the DDR, which is very costly, you try to split the compute in a way to do something similar to this, but in limited resources. And that's why we end up doing these techniques like vertical fusion and the like. At the end, when you are data bound, means you are dealing with large weights but generating small tensors. Then we are data bound. And then in this scenario, what we do kind of weight streaming. So instead of waiting for a big, all the weights, which are quite big to be loaded, we can load, just enough to start an operation and then start overlapping the next chunk of weight when we are processing those subtensors, and so on and so forth. So, and that's the kind. I mean, it looks like maybe straightforward, but it's far from that. When you take into consideration the memory hierarchy and all the constraints, for example. If you are splitting the layer, it's different when you are dealing with what we call non-mixing layers and mixing layers. If you have, for example, 1-by-1 convolution and you split in H and W, then you are fine. But when you have no 1-by-1 operation, then you have to deal with the overlapping area. And are you going to replicate the data and compute, or is the hardware ready to handle those type of situations? So here's an example of compiling tensor. So here, for example, as I said, we start with so the top you have a DDR, you have local memory, and at the bottom you have the compute element that I will show later. So at time 0 we have the weight in DDR. So the trigger DMA to bring the weight to the local memory. We have the input tensor with T0, the weight. So we are all set to produce the second tensor, which would be required for the next layer. Then we bring the second weight, and then we do the same thing and so on and so forth, until we generate the data. So that's, and this is kind of not optimal schedule. Why? Because you see that there is no overlap. We are waiting for DMA to finish, and so on and so forth. So the second case is a little bit more optimized, but with not much resource constraint. Then we try to overlap. So as I said, once at this point, so if at this point I am done with the data, I'm okay to start the DPU. Then I start it at the same time. I trigger the next DMA, and so on and so forth. So here I'm fully very optimal. There's no gap in my compute. But when you are dealing with small memory, then that's a problem. And this is where you can start splitting, the layers, and you bring, you try to process subtensors and bring as much data as you need for subtensors, and parallelize the compute and data movement. And you see what at the end you end up with. If you have a very complex or a very efficient compiler, you can converge to a scenario where you don't have limited resources, and that's the best compiler. So the best compiler is you reach the same level of efficiency with much less resources, and that's the challenge. So, and that's how I mean, the typical compute platform, or embedded, or what do you call edge AI platform compute architecture. So you have a number of processing elements. Those can be categorized or classified into different classes, or single class, or different clusters, or different hierarchies. And so we can list a lot of examples here. So and the tensor, the input tensor, which has H and W size, and you have the input channels, and then so the DPUs would be collaborating on processing the same tensor, and they, depending on what part of the weight of the network we are. If we are at the start, usually you have wide tensors, where wide shallow tensors means the channels are not that much, but the H and W sizes are quite big. So in this scenario, you are better off tiling in the space, and basically all the PPEs, if we are splitting in H and W, they would be all reusing the same weight, the same set of weights. So each PPE here, each processing element will require access to every single weight set here. If you are at the end of a network where you are the biggest dimension is the output channel, then we will be splitting the output channels between the PPEs. In such scenarios, you are going to split the weights. So each PPE will have access to the whole tensor, input tensor, but only part of the weight. And that's the logic of what to split. Are we going to stream the weight, or are we going to do kind of vertical fusion if you are at the start? So yeah, I don't know if how clear I made it for you guys, but yeah, you can ask me questions at the end, or you can reach out to me if you want to learn more about that. I've done a lot of stuff that I'm not mentioning here. So let me focus now on one advanced feature, which is sparsity. So sparsity, it's a simple concept, because it's a very old concept where the point is how we try to avoid to compute zeros, because doing convolutions, you are doing multiplications. If you have 0 elements, you don't need to compute them. But it's very hard to have a hardware architecture which leverage sparsity. And in general, sparsity can be leveraged in 4 different ways. So it can be leveraged in the weight in terms of memory footprint and bandwidth. Why? If I have 50% weight sparsity, then I will require half storage, half bandwidth. And if my hardware can skip the zeros, then I can leverage that for the compute. Same thing with activation, but the problem with activation is it's unpredictable. So anything in the weight is predictable because you have access to it at the compiler stage, and they are not changing during the inference. While on the activation side, things are much more complicated, and most of the existing platforms, they don't leverage it. Our Intel platform actually does that, and I work on this a lot, but not all of the platforms do have this capability. So you don't know how much sparsity you will have. A layer can produce. Sometimes you can. For example, if I have a network like YOLO v3, for example, where the activations is not using a kind of ReLU, but using leaky ReLU. Leaky ReLU doesn't generate sparse data. So in this scenario, you are better off not using triggering any activation sparsity. That's if the hardware leverages in the first place. While if you have a network with, for example, ResNet 50 or any conventional or most of the networks that use ReLU, usually you are around 40 to 50% activation sparsity. So it's good. It's good if the hardware itself can leverage it. But the problem is you can leverage it in compute. You can have a compute which can skip the zeros for activation the same way it does for weight, except maybe the complexity related to the compute is the fact that your processing element has to have the capability of generating sparse data. And but if you do this, you still cannot predict how big. You cannot predict how big would be the tensor. You cannot. Are you going to account for the worst case scenario or best case scenario, and accordingly? So it's quite hard to do it. So I put it. I didn't want to put it red here. Why? Because we have a platform that is equipped with all the hardware features that can leverage it. I have a design for kind of I have ideas, that how this can be solved. That's why I didn't want to put it red. But yeah, in the current hardware that I'm aware of, it should be red. So, for example, if we go if we talk about the Ampere architecture from NVIDIA, which is the latest technology they brought up, and the 800. So they have what they call you know, in the sparse world, you have two cases. You have either you go structured or like say block sparsity or fine grained sparsity. So NVIDIA came up with something which is in the middle, which they call it kind of fine grained structured, which means that you have blocks, but you have fine floating blocks. Let's say they require every four adjacent weight elements, 2 of them should be 0, and that's how they leverage sparsity. I think you can find there's a link here where you can find more details about that. But basically, this leverage only weight sparsity because of this 2 in 4 architecture. They cannot the maximum they can leverage is 50%. If you have 80% sparse weight, they still leverage only 50 because they skip only 2 out of 4 in the compute. So maybe the disadvantage is the fact that they require also always retraining or fine tuning. They cannot, for example, leverage the natural sparsity. Like, for example, if you take if the weights are already, when you train them, they are 10% sparse or 20% sparse. They cannot be leveraged. They have to go beyond the 50%. So that's why they require kind of constrained fine tuning. They have 12.5% overhead, which is always the case because they need to, for example, they have to store those sparsity maps, and those will take 12.5% of overhead. Which, although they claim that they have 2x benefit from sparsity, in fact they cannot. That cannot be true. The maximum is 37.5. So as such, if we go revisit our classification in previous slide, then we say that they leverage, the weight sparsity in terms of memory footprint and bandwidth because they just move they have packed or compressed data, and they leverage the compute for weight, but they don't do that for activation. So I have 3 minutes left. So now in this retraining, constrained retraining, as I said, they force what they do. They start with the trained model, and they do a kind of fine tuning by forcing the 2 out of 4 adjacent elements to be 0, and they compensate. And the fine tuning is there to compensate for the introduced errors, to bring the loss in accuracy to an acceptable level. But it is now sometimes it's hard to do that. Sometimes you don't converge, not because you don't have enough sparsity, but just because of the pattern of sparsity, where you have maybe the sparse data or the dense data are packed into into part of weight set and so on. So sometimes it would be hard really to reduce the error to an acceptable level. I have this is a patent I have proposed to do something, and that's an example of what one can do at every single level. You can do something to leverage the features of the hardware. In this scenario, what we proposed is to do kind of weight manipulation, non-intrusive weight manipulation, where it looks like a bit science fiction, but this is true actually. We can manipulate and change the order of the weight without retraining, and that's I forgot to put the link to the patent here, but I can share that with you. Okay, thank you very much. I'm on the spot. Thank you very much for your attention. Please let me know if you have any question.
Thank you very much for the presentation. It was very interesting to know about, especially concerning Edge AI, and it was so kind and generous from you, and definitely we learned a lot. There is a question in the comments. It says, is there a study that helps with designing hardware-aware models, or do you think this is impossible regarding the variety of HW platforms available?
So that's a very good question. Of course, they exist. I think what is key for to design or to train taking into consideration hardware, is to be driven by cost models. So for example, if we are doing retraining or we're doing sparsification, we can do it with kind of reinforcement learning, where you can force sparsity to reach certain level, and basically you base your reinforcement learning based on a kind of reward system, and that reward should be driven by what makes sense for the hardware. So basically that reward should be generated by a kind of cost model derived from the specification of the hardware, and that's yeah. So as a concept, this is what you need to understand. You need to understand how the hardware leverage the feature you want to optimize for, and you need to have the right model for it. And that if you have all of this, there will be always solution to design an efficient architecture, or train or have a kind of efficient hardware aware training for that feature.
Okay. Thank you very much for your answer. And also another small question, it will say, what are the requirements, or will we need to do a lot of changes when we move to edge AI, to changes concerning the model?
So that's yeah. So we need to depending on what are the targets, what is the target platform. Okay, so one extreme is I have a target platform which doesn't leverage sparsity, doesn't leverage low precision. It's always FP16, or you don't know how they are leveraged. Then there's nothing you can do. You have you need just to run nothing to do. But if you know your target platforms, what are the features of these target platforms, there are stuff you can do. An example, for example, you try to avoid adding layers, or if you have a choice between two layers, you want to put one which is leveraged well by the hardware. If you, for example, if you are deciding about the number of channels, output channels in layers, try to, if your hardware compute in multiple of 16, then you go for multiple of 16, and so on and so forth. So if you have a choice, of reducing, for example, the number of the size of layers, or trying to, for example, instead of having huge one layer, you can split it into finer grained layers that will be better fit for your hardware. Then you do so. So once what is key to all of this is how much knowledge you have about the platform and how much you can account for. If you have all of that, definitely it will help you to design an efficient network, or design a kind of a NAS system to converge towards something that makes sense for your target platforms. Or, as I said, also train or fine-tune the model to leverage certain features of the hardware.
Thank you. Okay, thank you very much for the answer. These were, I guess, all the questions.
I have another question, if I can.
Of course.
Okay. So it's about sparsity. If I understood, there are some hardware that accept a certain level of sparsity by compressing the tensors, right?
Yeah.
But what makes a hardware leverage this degree of sparsity and what doesn't?
So as I said, it depends on what leverage you are talking about. Is it compute or data movement or bandwidth or footprint? Yeah. So if you can, for example, if you don't have a feature, a compression feature, your hardware can still leverage that sparsity in compute. What I mean is that you can have a sparse tensor. You move the whole sparse tensor to your memory. You don't leverage the size, the sparsity in the footprint or the data movement, but your hardware can still leverage. Skip the zeros in that tensor. So you can the other way around. The other way around doesn't work. I mean, if you don't have sparsity, you cannot leverage anything there. But I think I don't think there will be a clear one answer to your question. You have, as I said, you have to understand what is the capability of hardware. For example, if we focus on NVIDIA, they have this pattern of 2 in 4. Then whatever you do, you cannot go beyond 50%. So if you are retraining, if you are fine tuning, your weight, so there's no point in going to 80% because at the end of the day, your hardware leverage only 50%. So just go to there. If we have a platform, for example, that Keynote of NVIDIA or of Intel, where you leverage fine-grained sparsity. In that scenario, any increase in your sparsity will translate into a gain. So not only from weight point of view, but also activation point of view. So in that scenario, your complexity, if you want to maximize the benefit, you have to have very complex fine-tuning, because your fine-tuning will not only be done only for weight, but also for tensor. You can force, but I mean, talking about the tensor itself, if you train a layer to generate certain level of sparsity, this is possible, by the way, yeah, and we do that. Mm-hmm. And that's activation sparsification. It is harder, but you can do it. But once you do it, I mean, does it make sense to do it for NVIDIA because they don't leverage it? Yeah, but it makes sense for example, for Keynote, which is Intel's platform. This is I think this is a topic which is worth offline discussion. If you can.
Yeah. Okay. Thank you very much.
Thank you.
Well, I guess Hajar's question was the last one. Thank you very much for answering generously all the questions, and also for being with us today and sharing with us. It was an honor and pleasure to have you. We really appreciate
Thank you very, very much again. Thank you.
Very much. So now for our third talk and our talk session for the AI Day, we are honored to have Ayoub Ben Isa. Ayoub Ben Isa is a graduate student from EZ SBA with a thesis on PPML, privacy preserved for machine learning. He has been working at OpenMind for more than a year and is now leading the homomorphic encryption team there. Today, you will talk about privacy preserving machine learning. And if you have any questions for him, also always leave them in the comments below. So welcome with us, Ayoub, and thank you for accepting our invite. We are pleased to have you.
Assalamu alaikum, and yeah, shukran for the invitation. التوك راح يكون بغد الدارجة الجزائرية. دونك راح نسي دابا نبارطاجي سلايدز. اوكي. اوكي. Je pense est-ce que oui slides?
Oui, je vois. Oui.
Okay. Donc, pour cette talk, on va privacy preserving machine learning en général. Nous allons avec une introduction et les motivations à utiliser le genre de technique. Après, راح نشوفوا des use case تاع machine learning ونشوفوا كيفاش privacy preserving techniques يقدروا ينتجروا هاد use case. Et après, on va détailler une des techniques que nous pouvons utiliser pour faire du PPML, qui est homomorphic encryption. Après, on conclut avec quelques notes, quelques idées que nous pouvons utiliser en PPML. Et next steps for anyone qui veut apprendre les techniques. Et bien sûr, à la fin, on aura un Q&A pour ceux qui ont des questions. Donc, نبدأ avec les motivations ou privacy preserving. Donc, privacy-preserving technologies are here to assist machine learning. هذا يعني باللي الجول تاعنا تاع machine learning مش راح يتبدل. أنا توجور حابين نتعلموا patterns على الداتا باش نقدروا نديروا classification, clustering ولا autre chose. دونك الجول تاع machine learning مش راح يتبدل. مي واش أنا حابين سيك ناجوتيو features للماشين learning process تاعنا. دونك الفيتشر هادو راح ناجوتيوهم concern privacy bien sûr. دونك peut-être أنا حابين نقدروا توجور نديروا par exemple l'entraînement تاع موديل mais sans vraiment accéder les données. ولا peut-être أنا حابين نديروا inference على input بلا ما ريالمون نشوفوا هاد الانبوت تاعنا. ولا كاين تاني لا possibilité تاع لا protection تاع الموديل. دونك une compagnie اللي peut-être دارت un entraînement avec des données اللي شراتهم ولا الموديل هذاك سي property. دونك ماهوش حابين peut-être يمدوه simplement مي حابين peut-être يبروتيجيو الموديل تاعهم. دونك ثاني بي بي ام ال يدخل ثاني في هاد لوك. دونك في هاد لي كا تقدر هكا مع الاول تبان اسي بيزار اننا راح نوتيليزيو لي دوني بور لونطالمون و بوندون لانفيرونس بصح اون ريالمون ماناش نشوفهم. دونك شغل سامبلومون تقدروا تيماجينيو بلي راكو تستفادوا من لي دوني انفيزيبل في البروسيس هذا. مي راح نديتايو ابري كومون سا مارش ان بو. راح نسيو نوتيليزيو ان اكزومبل تري سامبل في لي سلايد تاعنا اللي هو sentiment classifier اللي se base على الفيسز تاع الناس. دونك يدي اون ايماج تاع اون بيرسون و يقدر يقول اسك لا بيرسون از هابي ولا ساد ولا اوتر شوز. مي ابوبري سي ليكزومبل اللي نسيو نوتيليزيوه. دونك ان اكزومبل هو اننا حابين نديرو ان انطالمون على الفيسز تاع بزاف ناس بصح سي كومام اون دوني اسي بريفي. Donc, un exemple de PPML, c'est que nous mentalement sur Hadoop Faces sans réellement les voir. Donc, nous mentalement sur quelque chose qui est à peu près invisible. Donc, comme on peut voir sur le goal, nous allons toujours mentalement sur des données, mais on a bien réalisé une feature qui protéger quand même les faces tels que pour Hadoop, les gens qui sont dans le dataset. Une motivation très importante de l'utilisation de VPN, c'est user awareness. C'est parce que Kinas have rights down around privacy, ils vont être plus exigeants en termes de feature. Ça, ils vont faire des priorités selon des variables qui vont citer. Ça, il a lieu vraiment demander aux features c'est vraiment un indicateur اللي لازم vraiment يشوفوا vers هذا الفيتشر. Donc, user awareness around privacy est important. الناس يمكن aussi une compagnie vraiment effectuer les stratégies parce que les stratégies sont des offres différentes. Dès qu'on peut switcher vers différentes produits.
Hi, we are sorry. He is having problems, internal problems. I guess he's back, yeah. Can you hear me, Ayub? Okay,
Yeah.
that's Sophia.
Yeah.
Okay. So I let you share your slides again. Inshallah.
إلا بغيت تقدر تقول لي بدات نجي بروبليم ما حكمتش اكزاكتومون تشرح. Sorry, j'ai eu quelques problèmes de connexion, mais normalement ça va marcher mieux. Et la partie organizer, est-ce que c'est un peu mieux toi? Ou à peu près à quel moment tu fais ta machine? Ok. Donc, je dois trouver maintenant. Ok, donc, comme on a donc privacy preserving technologies are here to assist machine learning. Donc, le but de machine learning comme on a reste le même. Mentalement, clustering, mentalement tu as des modèles pour faire de la classification ou la clustering ou autre chose. Mais on a حابين نزيدو features اللي هي la protection de la privacy, que ce soit في le moment de training, في le moment de l'inférence ou pour protéger un modèle ان واحد يكون مونطري موديل وما شحال باغ اكزومبل الاركيتكتور تبان الويتس يبانو دونك هو حاب يبروتيجي الموديل تاعو اي دونك ليكزومبل اللي حنا نوتيليزيوه بور تاع لا بريزونطاسيون هذه سي سنتيمنت كلاسيفاير اللي يوتيليزي فيسز تاع بيبل باش يقول اسك راهم هابي ولا ساد و واحد نوتيليزيو هاد ليكزومبل وكل تاع لي ديفيرون يوز كيس. دونك تاني pour les motivations de l'utilisation de les techniques, donc l'users awareness. Donc c'est très important parce que les développeurs les applications ont des features à implémenter et ils vont faire des priorités à la des critères تاعهم. Mais إذا الusers تاعهم يخدموا بزاف على privacy, ils vont demander de plus en plus nos privacy techniques qui sont disponibles dans l'application. Donc au lieu de mettre pour ajouter une fonctionnalité جديدة capable de prioriser, ils vont ajouter au feature de privacy. Et donc c'est une des motivations que les techniques soient utilisées. دونك اوسي تاني لي كومباني مش حابين هاد الايامات لهم يخرجوا في النيوز انهم ما يبروتيجيوش برايفسي تاع اليوزرز باسكو الى اليوزرز تاعهم كما قلنا سون اكزيجون ماتير دو برايفسي يقدروا يسويتشو تري فاسيلمون فير ان برودوي كونكورون اي دونك راح يخسروا اليوزرز تاعهم اي un motivateur très important il y a regulations donc on trouve de plus en plus des lois sur le privacy strict et c'est très fort possible انهم يولوا encore plus strict في le futur qui des techniques de privacy preserving يولوا plus ready for production et donc نقدروا ناخذوا l'exemple تاع GDPR اللي est capable par exemple توصل حتى 20 millions d'euros ولا 4% تاع annual revenue تاع الكومباني capable يسورباسي à peu près هاد la somme إلا ما يكونوش compliant مع regulations تاع GDPR. Et GDPR c'est juste un exemple ما c'est pas vraiment applicable للجزائر mais peut-être qu'un jour on a des regulations faites le sens. Donc il est préférable que nos compagnies يكونوا compliant مع هاد regulations وينفستيسيو هاد الموني باش يديروا research ويديفلوبيو des techniques تاع privacy preserving. Donc يكونوا رابحين dans les deux sens. Donc يقدروا يبروفيتيو des données sans vraiment toucher à la privacy تاع اليوزرز تاعهم. Mais donc as product developer تقدر تسقسي روحك لا كيستيون تاع واش هو البينيفيتس انني نوتيليزي هاد لي تكنيك دونك ابار انك تكون كومبلاينت مع ريجوليشنز ولا اليوزرز تاعك يعني تعطي لهم واش كانوا حابين ان تيرم دو برايفسي اسك عندك اوسي فايده ابار هادو انك توتيليزي دي تكنيك باغي شغل الفايده اسي فونكسيونيل كنحبوا نقولوا ولا اسك par exemple le modèle tag يكون plus performant ou quand tu utilises des techniques pas et la réponse يعني elle est assez variable parce qu'en réalité c'est pas les techniques de privacy preserving les capables et attendre par exemple un modèle plus performant mais la confiance ou les techniques يقدروا يديروا ما بين companies تقدر انها تمد plus de performance للموديل كيفاه سي كو لي ميم لو كان ما كاش ريغوليشنز كاين بتات دي كومباني كونكورونت ولا ما يحبوش فريمون يبارطاجيو لي دوني ما بيناتهم باسكو بتات سي دي زيكسبيريونس يديروهم لوكال ولا سي دي دوني لو كان ان كونكورون يشوفهم يقدر باغ اكزومبل يديفلوبي اون ميور تكنيك عليهم مي دي تكنيك باراي يقدروا يسمحوا لدي كومباني انهم يكولابوريو باش هذا يقدر يستفاد من لي دوني تاع الاخر بصح سون ريالمون افوار اكسي ديريكت لي دوني دونك يقدر يستفاد انه يونطريني الموديل تاعو يردو بلو جينيراليزي مي سون ريالمون اكسيدي لي دوني تسمى الى باغ اكزومبل الداتا سيت هذيك فيها دي نون تاع لي كليون la somme اللي يخلصوها ولا سي دي اكسبيريونس سي دي تروك دي اكسبيريونس فارماسيوتيك ما يقدروش ياكسيديو لهم ديريكت مي يقدروا يستفادوا منهم لور دو طونطانمون ولا et donc ça débloque quelques problèmes à l'accès des données donc on sait que la donnée c'est l'essence de la machine learning et avoir des problèmes à accéder à des données de qualité est un problème assez ennuyeux qui tourne sur un projet de machine learning. Donc ça peut débloquer l'accès aux données qui peut directement avoir un impact à la qualité ou l'efficacité des modèles entraînés. Et donc on va commencer باش نهضروا على the use case تاع machine learning وكيفاش les techniques تاع privacy preserving peuvent intégrer هاد use case نبداو بالtraining. دونك نعاودو نولو l'exemple تاعنا توجور انا حابين نعطيو un sentiment classifier based on person's face. دونك هنايا capable يكون عندنا موديل ديجا انطريني وانا حابين نردوه خير sur les données تاع اليوزرز تاعنا ولا أنا حابين نونطرينيو un modèle from scratch based on les images تاع اليوزرز تاعنا. Donc dans les deux cas راح نسحقوا un accès les données. Donc هنا نهضروا على comment l'entraînement se fait généralement. Donc نسحقوا un accès les données تاع les utilisateurs تاعنا. Donc la solution la plus simple c'est que نضموا كاع les données في un serveur central من اليوزرز تاعنا ونديروا l'entraînement في هاد le serveur central. Et يعني هذا c'est un problème تاع privacy parce que chaque client aura besoin انه يبعث data تاعو en clair les serveurs pour faire l'entraînement. Bon هنا يقدر شغل في المومون تاع انه يبعث لي دوني يكونوا شيفري في la communication mais en réalité le serveur central يسحقهم quand même يكونوا en clair باش يقدر يتعامل. Et aussi هذا c'est pas juste un problème تاع trust ما بين اليوزر والسيرفر central parce que يقدر هو il lui fait confiance اليوزر il fait confiance للمود serveur central راح يدير training انه مش راح ياكسيدي مش راح يشوف ليماج en elle-même راح يدير l'entraînement mais qui assure بلي هاد le serveur central don't get compromised ou les données يتليكا ولا un truc pareil. Donc c'est pas juste une affaire de trust mais est-ce qu'on peut sécuriser le process تاع l'entraînement. Donc نقدروا نسيكوريزي on est sûr بلي y a pas de souci là-dedans. Et bien sûr كاين peut-être des cas où trust is also an issue بصح c'est pas le seul problème في هاد Et donc est-ce que نقدروا كيفاه نقدروا نردوا هاد البروسيس more privacy preserved. Donc هنايا on va essayer d'intégrer par exemple une technique de privacy preservation. Donc maintenant au lieu de نجيبوا data le modèle on va essayer d'envoyer le modèle لوين راهي la donnée. Et هذه on parle de federated learning. Donc qu'est-ce qui se passe pendant le training process c'est que serveur يبدا يبعث الموديل initial اللي انا نشوفه هنايا en bleu لشاك كليون وشاك كليون عنده داتا سيت لوكال دونك انا نريبريزونتيها بديفيرونت كولور وشاك كليون va entraîner الموديل هذاك initial على الداتا سيت اللي عنده en local. Donc ça va créer un modèle جديد et راهم représenter la couleur تاع الموديل اللي حطوا لي السيرفر est représentée selon la couleur تاع الداتا سيت parce que هذاك الموديل contient des updates et ils sont spécifiques للداتا سيت. Et donc chaque client ينطرين على local data set تاعو يبعثها للسيرفر. السيرفر va faire une agrégation تاع كاع les différents modèles capable juste يحسب l'average تاع الويتس تاع chaque modèle اللي جا من عند الكليون ودونك يولي عنده un nouveau modèle اللي يولي الموديل initial تاع l'itération الجايه تاع federated learning. دونك هذا البروسيس يقدر يتعاود plusieurs fois. دونك كل ما نبعثوا موديل initial نديرو نجيبوه نديرو l'agrégation c'est une itération تاع federated learning mais on peut répéter ça plusieurs fois. نقدروا نشوازيسيو différents clients chaque itération etc. Mais هنايا شغل le mécanisme تاع la protection des données est très simple. C'est que juste au lieu de la donnée تروح لun serveur elle va rester في بلاصتها et le modèle يتونطرينا وين راهي la donnée sans vraiment bouger la donnée من راهي stock. Donc هنايا ما زغدناش la donnée mais كاينه une question qui peut se poser c'est que est-ce que هاد الموديل هاد الابديتس اللي يولوا للسيرفر يعني نشوفهم par exemple en vert jaune et rouge ما راهوش يكونتوني دي انفورماسيون اكثر من اللازم على الداتا سيت تاع الكلاينت. دونك ايماجينون كو هاد الموديل هذا اللي عاود ولا راهو جوست يحفظ الداتا سيت تاع الكليون et donc en réalité كشغل بعثنا الداتا. دونك هذه سي اون كيسيون كي دوا سبوزي و لازم نريبونديو ونشوفوا اسك هاد لو موديل ماهوش برك يحفظ ويعاود يولي بالسيرفر باسكو سي هكاك توليك شغل بعدنا لا دوني. Donc, pour répondre à ces questions, la question عندي تاع واش نقدروا فريمون نعرفوا كي نشوفوا هذاك الموديل اللي ولا السيرفر. دونك كاين ديفيرونت اتاك، بصح راح نشوفوا دو تيب برينسيبو. كاين membership inference attacks و data reconstruction attacks. دونك membership inference attacks البوت تاعهم انهم يريبونديو على لا كيسيون اسك هاد الداتا بوينت كان في ترينينغ داتا سيت. في ليكزومبل تاعنا اون اتاك كيما تاع هاد لو تيب البوت تاعها انها تحكم اون ايماج دونك person's face و تفيريفي اسك هاد ليماج كانت بارت في ترينينغ داتا سيت ولا لا. دونك اسك هاد لا بيرسون كانت part of the training process. Data reconstruction attacks البوت تاعو يريكوفريو some of the training inputs. الموديل هذاك اللي كان رايح للسيرفر دونك اللي اونطرينا على داتا سيت سبيسيفيك نقدروا نديروا ريكونستراكشن تاع كلكو انبوت نديروا ترينينغ. دونك هنا سي لو كا وين باغ اكزومبل الموديل راهو فريمون يحفظ لي دوني اللي كاينين في الترينينغ تاع الريزو. دونك الا نعاودو نبعثو ان موديل اللي اونطرين على داتا سيت اللي كانت بروتيجي كوتي كليون بصح اون اتاك باراي تقدر تريكوفري كاع الداتا سيت. دونك شغل بعثنا الداتا سيت اون با فريمون في ولا بروتيجي داتا سيت اللي كانت عند الكليون. اي هاد لي تيب داتاك عندهم des settings différents. Donc, on parle de black box and white box settings. Donc, في black box settings, l'attaquant ما يعرف غير الانبوت والاوتبوت تاع الموديل. دونك باغ اكزومبل عنده API وين يقدر يبعث انبوت ويرسيفي الاوتبوت تاع الموديل. في الوايت بوكس سيتينغز عنده ميم لا كونيسونس تاع الموديل كيفاه داير دونك لاركتيكتور والويتس تاع الموديل. Et bien sûr, plus on a des informations, plus le genre d'attaque et a des chances de connaître. Et malheureusement, dans le federated learning process, on a le white box parce que هاد السيرفر اللي راهو يبعث الموديل لي كليون باش يديروا الترينينغ على الداتا تاعهم راه على بالو لاركتيكتور وراهو يشوف الويتس كامل. دونك راهو اون بوزيسيون انه يدير هاد لو تيب داتاك افيك un pourcentage de réussite كبير على لو كان في البلاك بوكس. دونك هاد لو تيب داتاك يعني c'est bien de se poser la question est-ce qu'on est vulnérable quand on fait federated learning ou est-ce qu'on peut ajouter des layers pour sécuriser encore plus pour la réussite de la data qu'on utilise. Et donc là on va essayer d'intégrer une autre technique qui est secure aggregation. Donc le but تاع السيرفر اللي حيدير l'entraînement et انه يبيلدي هذاك الفاينل موديل اللي يكون اونطرينا على les différents datasets اللي هم عند اليوزر. Donc ce n'est pas important ليه انه يشوف individual updates غير لو حاب يدير une attaque كيما اللي شفناها من قبل. Sinon il peut se contenter غير بالفاينل موديل. Donc une technique اللي اسمها secure aggregation اللي كنهضروا عليها غير black box انها تدي individual updates تاع اللي هم جايين من عند الكليون والindividual updates هادو يكونوا en quelque sorte نقدروا نقولوا شيفري ولا invisible. دونك مانيش نشوفوهم ريالمون مي نقدروا ندخلوهم في البروسيس تاع secure aggregation. والاوتبوت تاع secure aggregation سي الافريج تاع هاد الانديفيدوال مودلز. اي البروسيس هذايا تاع secure aggregation يقدر يتمبلمنت avec different techniques كيما secure multi-party computation ولا homomorphic encryption ولا même des techniques hardware تاع trusted execution environment. Mais sans parler de comment ils peuvent être implémentés, l'idée comme on a c'est de protéger individual updates ونوصلوا ديريكتومون للجول تاعنا اللي هو الاجريجيتد. دونك هنا بيسك ما نقدروش نشوفوا الانديفيدوال ابديت، سي با فاسيل اننا نديروا لي زاتاك تاع داتا ريكونستراكشن ولا ممبرشيب انفيرنس ابديت. اي une autre تاني solution c'est que وحنا واش قلنا que par exemple الموديل اللي يكون يحفظ vraiment les données اللي هم كاينين في training data set. Donc il est plus vulnérable انه data reconstruction attacks يكونوا possible. Et الموديل كيكون يحفظ training data set, généralement on parle de overfitting في الماشين ليرنينغ community. والماشين ليرنينغ community عندها des solutions contre overfitting, par exemple on utilise regularization. بصح البرايفسي كوميونيتي تاني عندها دوت سوليوشن اللي عندهم دوت غارونتي بارابور للبرايفسي. دونك اون دي تكنيك اللي نوتيليزيوها باش نقصوا من هاد الاوفر فيتينغ ولا الحفاظه تاع لي دوني سي differential privacy. و par définition differential privacy يعني الى لا ديفينيسيون زعما ماتيماتيك هي اننا لو كان نحكموا داتا سيت ونديروا مونطالمون تاع الموديل تاعنا ونعاودوا لو ميم بروسيس بصح الداتا سيت تاعنا نحو منها واحد من داتا بوينت راح يكون عندنا لو ميم موديل افيك اون probability à peu près égale. دونك واش هذا يعني انه واحد من الداتا بوينتس اللي عندنا في الداتا سيت ماشي راح يكون عنده امباكت كبير على الموديل فينا. دونك باغ اكزومبل في ليكزومبل تاعنا تاع سنتيمنت كلاسيفيكيشن ليماج تاع اون بيرسون نحطوها ولا نحوها من الداتا سيت ماشي راح تكون عندها ان امباكت كبير على الموديل فينا. ان موديل اللي راهو يحفظ كاع ترينينغ داتا سيت نورمالمون كي تاجوتي له تصويره جديده دونك هذيك الحفاظه va vraiment impacter le modèle فينا. بصح differential privacy il donne la garantie تاع انه ان input اللي راهي في الداتا سيت تاعنا مش راح تكون عندها امباكت كبير على الموديل فينا. اي دونك differential privacy هنا كيفاش تخدم سي par l'addition تاع noise during different stage تاع training process. وراهي هنايا شغل تبان avec des couleurs différentes في الموديل حنا نبعثوه للسيرفر. دونك au lieu de ما نحفظوا كاع الداتا سيت on va avoir des updates qui sont un peu noisy en quelque sorte. Donc il y aura un petit impact à l'accuracy peut-être تاع الموديل mais on va avoir des garanties انه الموديل ما راهوش يحفظ chaque input راهي عندنا في الداتا سيت. Donc des attaques comme data reconstruction ou la membership inference vont avoir moins de succès. Donc on a fait une differential privacy, secure aggregation. Donc c'est des techniques qui peuvent être utilisées en parallèle. Donc واحدة ما تمنع الأخرى. Et ils peuvent ajouter plus de sécurité concernant privacy تاع الداتا سيت اللي حنا نوتيليزيو. Et donc c'était le training use case et quelques techniques اللي نقدروا نوتيليزيوهم شويه لي تكنيك تاع privacy preserving نقدروا نانتيغريوهم في هذاك اليوز كيس. On va plus parler à l'évaluation. Et donc, généralement, l'évaluation qui نديروها c'est que par exemple يقدر يكون عندنا الموديل تاعنا ولا حنا نهضروا على لو كاوين نفتشيو par exemple الموديل من database. نقدروا نهضروا par exemple sentiment analysis sentiment classifier تاع ليكزومبل تاعنا راهو ديفلوبي بار اون كومباني اكس اند حنا حابين نديرو انفيرونس. دونك on va commencer par télécharger le modèle ou نديرو l'inférence عندنا localement. Mais pour des modèles qui sont assez grands ou des modèles propriétaires, c'est pas toujours possible ان نديرو هاد l'opération. Donc c'est pas possible نجيبو un modèle ونديرو عندنا الى الموديل est vraiment grand, peut-être ما عندناش الهاردوير requis باش نديرو l'évaluation. ولا الموديل en lui-même يقدر يكون un produit payant. Donc مش راح نديرو l'évaluation localement, mais donc راح نسحقو peut-être نبعتو لا دوني باش نديرو l'évaluation. ما نقدروش نديروها عندنا localement. بس كي نديرو localement on est sûr que la donnée تاعنا ما تخرج. بصح لو كان le modèle ما نقدروش نجيبوه باش نديرو l'évaluation localement, لازم نبعتوه لان serveur à disque. Donc كما قلنا le modèle peut être propriétaire ou un service provider اللي يدير l'évaluation et peut-être هو يخلص علينا par every inference. So لازم نبعثوا لا دوني. mais نبعثوا لا دوني ça veut dire que بعثنا par exemple الفيس تاعنا ولا بعثنا الفيس تاع une personne et ça peut être un problème تاع privacy. Donc كيف نقدروا à peu près use case تاع l'évaluation نعطوه more privacy preserved. Donc هنا راح نهضروا plus شغل على en quelque sorte general framework بلا ما نهضروا على une technique spécifique parce qu'il y a plein de techniques cryptographiques qui peuvent faire le même boulot la secure evaluation. Les protocoles peuvent être implémentés différemment en utilisant plusieurs round واحد. Mais l'idée générale c'est que la donnée va être chiffrée localement avec une clé locale اللي غير حنا نقدروا نديشيفرو la donnée et la donnée هذيك chiffrée تروح عند service provider اللي راح يدي لا دوني شيفري. دونك ما يقدرش ريالمون يعرف ولا يشوف ليماج اون elle-même, mais quand même il va être capable انه يدير l'évaluation عنده. دونك هنا on parle donc le service provider عنده un modèle qui est déjà entraîné tel l'inférence ou même le résultat اللي يكون عنده au final il est aussi chiffré ويبعث le résultat للuser ou le client au final يدير le déchiffrement ويقدر يشوف الريزلت تاعو. دونك هنايا عندنا une protection تاع côté client, donc la donnée تاعو n'est pas exposée, وعندنا ثاني une protection côté service provider اللي راهو عنده un modèle اللي peut-être ماهوش حابين ندو كما قلنا. دونك عندنا deux protections des deux côtés. هاد لو كان نوتيليزيو هاد le framework. Et donc, on n'a pas parlé de techniques cryptographiques spécifiques. Bon, à part, c'était juste un petit truc de differential privacy. Là, on a fait les détails. Mais on peut donc parler, par exemple, d'une technique cryptographique ayant homomorphic encryption. Et par exemple, d'implémenter l'inférence sécurité. Donc, homomorphic encryption, c'est quoi le problème اللي عندنا علاش نحب نوتيليزو homomorphic encryption في machine learning ولا other sort of computation? C'est que data is encrypted in transit, تسمى la donnée est chiffrée في المومون تاع la communication. Donc كاين نبعثو des données sur internet, c'est généralement chiffré même في la communication. Donc واحد يكون في الوسط ما يقدرش يشوف la donnée. Ou la donnée peut aussi être chiffrée في المومون تاع stockage. Elle est stockée في une base de données, elle est chiffrée au moment تاع stockage. Ça fait le moment تاع computation باش نديرو l'évaluation باش نديرو mentalement, on a toujours besoin اننا نديرو le déchiffrement. هادي sont utilisés en homomorphic encryption. بصح واش homomorphic encryption هي حابة اننا حنا en tant que users نأمنو, c'est que computation تاني can be performed on encrypted data. Donc ما نسحقوش نديرو الديشيفرمون قبل ما نديرو الكمبيوتيشن تاعنا. Donc هذه سي واش الهومومورفيك encryption providers. بصح وين رانا واصلين حتى الدرجه مع homomorphic encryption سي با فريمون جينيريك دونك ماشي اي كومبيوتيشن تقدر ديرها على داتا كي ني با شيفري تقدر ديرها على دي دوني كي سون شيفري بصح كاين دي يوز كيس هنا اون فا بارلي بريسيزيمون دو ماشين ليرنينغ لي يقدروا يتمبليمونتاو بالهومومورفيك دونك سي با جينيريك ماشي اي حاجه تقدر ترونيها في سي بي يو سور دي دوني تقدر ديرها sur des données chiffrées. Mais on va se concentrer sur ce qui est pratique, ce qui est fait, et ce qui est possible à implémenter dans le homomorphic. Donc, pour récapituler, donc, je vois le homomorphic encryption, c'est que on a deux circuits, على la droite واحد على la gauche. على la droite راهو يدي deux nombres x et y ويدير juste l'addition, donc c'est un circuit normal يدير على des données non chiffrées. وعندنا un circuit équivalent à la gauche qui fait la même chose ça sur des données chiffrées. Donc au lieu de prendre x et y dès le début qui راهم non chiffrés, on commence par les chiffrer. et هنايا نقدروا نبعثوهم من un serveur اللي هو حيدير je crois que plutôt à toilette. Donc, sur la gauche, on a un circuit équivalent qui dit le chiffrement après l'addition sur des données chiffrées. Donc, moi, je chiffrer x et y, mais à la base, exactement où je suis. Donc, l'exemple x est un 5 et y est un 3. Moi, je dis le chiffrement, mais à la base, réellement, où je suis l'addition. On dit l'addition seulement sur des données chiffrées. Et le z, le résultat de l'addition, c'est aussi une donnée. Sorry again. Toujours problème. Ok, je crois que je me sens maintenant. Donc, je vais essayer de le faire à deux slides. Donc, on va juste utiliser l'exemple du graphe de droite, l'idée de l'addition sur deux nombres x et y. On va dire juste x est égal à 5 et y est égal à 3. Donc l'addition terme, c'est juste 8. Donc à la droite, c'est le circuit simple, c'est le calcul des données en clair. Et sur la gauche, on a un circuit qui fait le calcul des données chiffrées. Donc après le chiffrement de x et y, on a l'addition sur un 5 et un 3, mais on a l'addition sur deux nombres chiffrés. On a exactement le résultat c'est z, normalement c'est 8, mais après l'addition, on a les z c'est 8. C'est juste une donnée chiffrée, on ne sait pas réellement où est le résultat de l'addition. Mais au moment où on a le déchiffrement, le decrypt gate, on a x plus y qui est 1. Donc, ما فوق ما تحت l'encryption وقبل الديكريبشن c'est du calcul mais c'est du calcul invisible. On ne sait pas واش هما les données réelles اللي نديرو الكالكول عليها. على بالنا بلي نديرو في l'addition mais ما على بالناش واش هما الانبوت وما على بالناش واش هما الاوتبوت. هذه هي l'idée تاع homomorphic encryption. Et donc, il y a différents types de homomorphic encryption algorithms. Donc, sur la droite, on a un exemple d'un circuit qu'on utilise pour différencier les différents types. في السيركوي هذا نشوفوا بلي كاين دي ملتيبليكاسيون وكاين دي زاديسيون. دونك الانبوتس تاعنا هما اللي هم من الفوق y x سي 3 و لو ريزولتا اللي هو قاعد تحت. لو تيب الاول اللي هو partially homomorphic encryption يقدر يفالوي دونك يدير هنايا بيان سور سور لا droite تاعنا ماناش نبينو لا بارتي تاع شيفرمون بصح x et y سي دي نومبر شيفر. اوكي دونك partially homomorphic encryption راح يقدر يفالوي لنا دي سيركوي اللي فيهم ان سول تيب تاع الجيت. دونك ان سيركوي كيما اللي هو عندنا في لا دروات ما يقدرش يتمبليمونتا افيك ان الغوريثم تاع partially homomorphic encryption باسكو هاد لو تيب يقدر يكون فيه غير يا لاديسيون يا الملتيبليكاسيون بصح با لي دو باسكو لو سيركوي هذا راه يوتيليزي بوث اديشن ملتيبليكيشن. دونك RSA الناس اللي يعرفوا الالغوريثم RSA يقدر يكالكولي الملتيبليكاسيون على دي نومبر شيفرين مي ما يقدرش يدير لاديسيون. ان الغوريثم واحد اخر اسمه بيري يقدر يدير لاديسيون مي ما يقدرش يدير لا ملتيبليكاسيون. ان اوتر تيب اللي هو somewhat homomorphic encryption يقدر يدير لنا الكالكول تاع لي دو gates multiplication والaddition بصح يورا دي ليميتاسيون. باغ اكزومبل نقدروا الالغوريثم لي زالغوريثم تاع هاد لو تيب يكون عندهم دي ليميتاسيون على لو نومبر دو ملتيبليكاسيون اللي نقدروا نديرو. باغ اكزومبل une seule multiplication, deux multiplications ou là le nombre de multiplications dépend des paramètres تاع l'algorithme. Donc هنايا c'est vrai. هذا هاد لو تيب est ce qui est généralement utilisé في machine learning parce qu'il est pratique et aussi des fois moins coûteux que un fully homomorphic encryption. Mais bien sûr, recherche في الدومين تاع homomorphic encryption est très avancée. Donc الناس تاني commence à utiliser fully homomorphic encryption. Donc fully homomorphic encryption c'est vraiment l'idéal اللي يقدر يخلي الناس يديروا any kind of computation sur les données chiffrées. Donc يقدر يكون عندنا multiplication additions without like limitations. و multiplication و addition gates نقدروا نimplémenter des layers تاع machine learning convolution linear layers etc. Donc هاد لي ديفيرون تيب علاش نصحوا نعرفوهم باسكو كيما قلنا دونك باش نديرو ايفالواسيون تاع موديل تاع ماشين ليرنينغ كاع الكونفولوشن ولينير لايرز يقدروا يترادويزاو ملتيبليكاسيون اي اديسيون سولمون اي بيسك نسحقهم في زوج دونك partially homomorphic encryption ماشي ساهل باش نوتيليزيوه في ماشين ليرنينغ. دونك نقدروا نحو somewhat و fully. لا ديفيرونس ما بيناتهم سي كو un modèle qui est assez deep, donc deep neural network تاخد de base net ولا il fait plusieurs opérations, plusieurs multiplications, des fois il nécessite l'utilisation de la fully homomorphic encryption. C'est des use cases اللي فيهم des modèles qui sont assez اللي فيهم peut-être two linear layers, زعما convolution two linear layers يقدروا يتimplémenter des algorithmes de type SHE. Donc نسحقوا نعرفوا les types الكوست تاع لي ديفيرون تيب قبل ما نوتيليزيوهم في ليفالواسيون تاع ماشين. دونك اي جوست هنايا مانيش حاب بزاف نديطايي باسكو سي با ان توك تاع كريبتو مي سكي فور ريتنير من هاد لي تيب سي كو الاس اتش اي هو اللي عنده des opérations qui sont moins coûteuses à la fully homomorphic encryption et les plus pratiques en ce moment à la FH. Mais le FH bien sûr يقدر يكون plus coûteux des fois mais il permet de faire de l'évaluation des modèles qui sont plus اللي فيهم plus de layers que واش نقدروا نديروا بال SH. Donc, juste très rapidement, parce qu'on a خرجت شوية على الوقت. الانترنالز تاع morphic encryption سي كيما اي الغوريثم تاع شيفرمون كاين لابارتي تاع جينيراسيون دو كلي public evaluation secret دونك لي الغوريثم تاع شيفرمون باغ اكزومبل على اس ا اس نسحقو غير public secret key دونك سا ديبون asymmetric ولا symmetric بصح سكي فو retenir سي كو le morphic encryption généralement il encapsule هذيك لا دوني x ولا y هنايا sur deux couches donc une partie qui est représentée en noir c'est une partie اللي تقدر تنحى بالsecret key et كاين la partie ديك violet اللي ce qu'on appelle noise donc وهاد les deux couches vont en quelque sorte cacher la donnée utile اللي راهي مخبيه داخل la donnée chiffre et donc au moment تاع l'addition ou la multiplication راح نجوتيو ce qu'il y a comme données encapsulées à l'intérieur où il prend les couches externes les en noir تقدر تنحى بالsecret key في المومون تاع decryption et la partie violet اللي هي النويز هنا c'est très important de penser à comment gérer النويز تاعنا et c'est généralement ce qui engendre la limitation هذيك تاع SHE donc parce que لو كان هذاك لا كوش تاع النويز تكبر بزاف il sera pas possible اننا نستخرجوا هذيك لا دوني اوتيل اللي هي اكس y في المومون تاع الديشيفر donc هذه c'était juste pour donner une idée واش comment les algorithmes تاع morphic encryption fonctionnent en quelque sorte mais c'est pas vraiment important les يسحق l'utiliser en tant que data scientist يقدر يفهم غير comment ça marche juste في النيفو تاع هاد le circuit donc باللي on peut faire le calcul sur des données chiffrées faire l'addition multiplication et puisque les modèles تاع machine learning يقدروا لو كان نبريكيو كاع layers تاعنا convolution linear layers نقدروا نكونسترويزيوهم غير multiplication addition donc نقدروا نutiliser morphic encryption pour faire l'évaluation donc au final pratiquement le même framework اللي هضرنا عليه من قبل sauf que هنايا c'est vraiment un route of communication وقبل قلنا باللي en utilisant une technique différente نقدروا نسحقوا plusieurs rounds باش نديروا كاع هذيك l'évaluation sécurisée en utilisant morphic encryption نسحقوا غير public key and secret key اللي يبقاو bon public key تقدر تروح للموديل owner secret key تبقى côté client au début كاع نديروا لو chiffrement نبعثوا لا دوني للموديل اونر الموديل اونر يقدر يوتيليزي SHE ولا FHE باش يدير ليفالواسيون اي يبعث لو ريزولتا شيفري للكليون اللي يقدر يوتيليزي السيكريت كي باش يريكوبيري لو ريزولتا فينال donc pour conclure donc privacy preserving techniques doesn't come at no cost plus précisément je peux نقدر نهضر plus على morphic encryption هنا spécifiquement parce que par exemple une évaluation تاع modèle تاع machine learning اللي تندار en quelques millisecondes sur des données non chiffrées capable تاخذ des secondes voire même des minutes على des données chiffrées donc le cost تاع l'implémentation de cette technique تاع privacy preserving c'est pas juste شغل ناجوتيو الفيتشر بصح is it really worth it انك تخلي اليوزر باغ اكزومبل يستنى المومون تاع هذيك ليفاليواسيون اسكو اليوز كيس تاعك يقدر يسبورتي هذا دونك سي تري امبورطون de voir si c'est possible et si c'est pratique d'utiliser le genre de technique donc c'est pas toujours pratique انك تutiliser et puisque شويه هضرنا شويه على morphic encryption juste شويه mais puisque c'est vraiment coûteux كما قلنا من millisecondes نقدروا نطلعوا les secondes il y a beaucoup de travail انه ينخدموا des compilateurs ولا hardware accelerations باش يعاودوا يهبطوا l'évaluation même sur des trucs chiffrés sur des données chiffrées seulement des secondes et puisque c'est aussi compliqué pour un data scientist انه au lieu de يبقى يخدم غير بالconvolution و linear layers اللي يعرفهم يبقى يخمم كيفاه يمانيبيولي دي دوني شيفري كيفاه peut-être يدير des circuits équivalents يقدروا يفاليو هاد les circuits. Donc الكومبايلر هيعاونوا انه الداتا ساينتست ما يشوفش كيفاش يوبتيميزي مي سولمون يكونسونطري على لوتيليزاسيون ديال الكونفولوشن تاعو يدير اللاير تاعو. هذا اي هنا هضرنا غير على هوموفيك انكريبشن بصح يا دو تكنيك كيما secure multi-party computation which are worth exploring because زعما في سبيس تاع privacy preserving c'est bien de connaître plusieurs techniques parce que des fois ils peuvent être intégrés ou un protocole un peu plus efficace que d'utiliser une seule technique. Donc c'est pas intéressant de se concentrer à une seule technique, mais c'est aussi intéressant de voir ce qu'il y a comme autre alternative. Et pour les gens qui sont intéressés ils essaient d'explorer privacy preserving machine learning ou AI. Donc كاين une série de cours اللي ينترودويزيو من الديبي تاع سي كوا البرايفسي وعلاش نسحقوها اكسيتيرا ويورا une suite تاع لي كور كي ديتاي homomorphic encryption, secure multi-party computation et les différentes techniques un peu plus en détail على واش شفنا اليوم sur le cours تاع OpenMind اللي حيتريليزا. Donc ça serait bien comme c'est une bonne next step على هذا التوك اللي ما ديتايناش كاع بزاف sur les différents types. Et avec ça je crois que it's un peu plus de temps like ask me anything.
Thank you and for the presentation. I really couldn't الوقت mais it was interesting. Thank you. Just question in chat if you could briefly answer. If a company wants to migrate to the use of PPML techniques in their products, do they need to reconstruct their solutions with a new data workflow and using PPML techniques from the beginning, or there are ways to integrate them to already existing solutions and make them more privacy preserving?
Okay. Donc, il a une compagnie par exemple عندها déjà des solutions عندها peut-être des modèles اللي راهي provider en tant que API, donc ça fait partie de leur produit. Donc هنايا it's worth كما قلنا like evaluating إذا it's really worth it ولا est-ce que ça va être pratique أننا n'implémenter des techniques. Et deuxièmement ça dépend aussi des techniques de privacy preserving اللي حنutiliser. Donc la majorité اللي هم يديفلوبيو لي تول هادو عندهم un but très important اللي هو الادوبشن تاع هاد التولز وباش اليوزرز يادوبتيو هاد لي تكنيك ils essaient le maximum انهم هاد لي تكنيك يقدروا ديريكتومون ان موديل اللي يوتيليزي par exemple convolution linear layers يقدر نديرو لا كونفرسيون ديريكت pour l'utilisation تاع لي تكنيك تاع privacy preserving technologies. Ça c'est pas toujours le cas. Donc, il y a peut-être des opérations qui ne sont pas très simples à implémenter dans le homomorphic encryption ou là, secure multi-party computation. Ou des fois, les modèles nécessitent un petit changement. Par exemple, au lieu de mettre contre reload activation function dans le modèle TR, tu auras besoin d'utiliser une autre activation function. Ou dans le cas, donc, il a de l'architecture du modèle TR, tu auras besoin peut-être d'entraîner le modèle dès le début. Donc ça nécessite انك تعاود تخدم على الكوتي machine learning باش تقدر تutiliser les techniques. Mais donc ça dépend vraiment على الموديل على اليوز كيس. Des fois لازم تعاود تخدم الموديل تاعك machine learning ولا des fois tu peux directement intégrer des techniques تاع privacy preserving. Donc ça dépend vraiment le modèle et les contraintes على la technique اللي راح تutiliser.
Merci, thank you for answering. J'espère que j'ai la response back. Thank you very much, Annie, for accepting our invitation and being here with us. So you took the time to present the talk. It was interesting. Thank you.
Thank you. Thank you for the invitation.
It was a pleasure. Now, last but not least, for our fourth talk, we have Abderraouf Gassem. He is a PhD candidate at l'IRIS ENS à Lyon, alumni Easy Algiers, former development department manager at School via Algiers, and then the ambassador in Algeria. Today, Abdurraouf's talk will be an introduction to graph deep learning. As always, don't forget to leave your questions in the comments. I'll try to forward them later to him. Welcome with us, Abdurraouf, and thank you for accepting our invitation. Glad to have you. You are muted. I can't hear you.
And now you can hear me?
Yeah.
So I was saying thank you for the invitation. Assalamu alaikum. Hello, everybody. I'm going to share my screen. Tell me if it's okay. You can see the shared screen?
Okay. Yes, yeah, yes.
So let me introduce myself. I'm Abdurraouf Gassem. I graduated from EASY last year, and now I'm pursuing a PhD at INSA Lyon in l'IRIS Lab. And today I'm going to talk a bit about graph deep learning. So I would like to start with some statistics about keywords from ICLR, which is a conference to publish about deep learning advancement. You can see that GNNs are a subject of interest, and GNN stands for graph neural networks, which are a subcategory of neural networks that deal with the graph structured data. So via this presentation, we are going to see why we need this subclass of neural networks, why this sudden interest, and in which way these neural networks are special. So it goes without saying that deep learning has revolutionized many fields, and the credit goes to the neural network, the neural networks, which take a vector as input and adjust the inference output based on a learning process, which is the backpropagation. Please note that a vector is a linear data structure with fixed size that can be manipulated with a large set of mathematical operations. So with this way, it was possible to design many neural network architectures. And when people wanted to extend the use of neural networks to images, they started with converting the image into a vector in this way. So by squeezing the matrix representing the image. And they got some interesting results, but soon enough, a necessity appeared. And I'm referring to defining operations to deal with the whole image. Can you hear me?
Yes, but we are not seeing the slides.
Really?
We are just seeing the first one. Okay, now it changes.
Okay.
Okay.
So this is the slide where I talked about squeezing an image into a series of vectors, and I was saying that with this way to apply neural networks on images, they got some interesting results, but soon enough there was a necessity, and I'm referring to defining an operation to deal with the whole image before feeding it into a neural network, and this without breaking it into concatenation of vectors. Maybe I should move to Google Slides to be able to share in full screen. Moment, please. Can you see the can you see the slide?
Yes.
Good. So what was I talking about? Yes. I was saying that an image is represented with a matrix, which is a regular data structure with a fixed size, which is an important element, and we will see why soon enough. So I was saying that since the image is represented with a matrix, there was already a mathematical support to let a neural network have a matrix as an input and thus have an image as an input. And this was possible thanks to convolutions. And one of the reasons convolutions were introduced is that breaking the image into vectors leads to a loss of structural information. In other words, in an image, when a certain pixel is put besides another, it's for a reason. And there is an information to be extracted from this arrangement in order to make a proper inference. And that's what convolutions filters are here for. They make it possible to extract this local relationship with which is defined in the 2D dimensions of the matrix and lost when the matrix is squeezed into a linear vector, because the pixels will be separated from each others. And so dealing with operations on the original representation of the image without altering it gives us a vector to feed to the neural network. So we come back to the original input needed by a neural network. But the vector we get it with the maximum amount of useful information being aggregated in it. And this vector can be seen as a new representation of the original image being learned via the convolutional operation. So the first part of a CNN is doing a representation learning. So now let's speak about graphs. Actually, the same problem comes over, and which is we can't feed a graph to a neural network unless it is represented as a vector or a matrix. And the problem is a graph is the most general data structure. It is composed of discrete entities, namely a set of nodes, which are connected to each other in a way that reflects their relationship. Besides, every node and connection can be associated with a set of attributes. For example, this is a neural network. This is a social network, which is represented by a graph, where the nodes represent people and if two persons are linked, it means there is a relation of friendship between them. And every person, as you can see here, every person is associated with a set of personal information, say age, home address, school they attended to, etc. And every connection can be associated with a date, for example. So we can see clearly that there is not a trivial way to convert the graph to a vector, or to convert the nodes to vectors and feed them one by one to a neural network. It's true that the list of connections can be converted to an adjacency matrix like this, and the attributes are stored in a matrix. So one might suggest that we actually have a vector representation for every node, and so we can use it as an input to a neural network. The truth is, this vector representation of a node is not consistent, because there is no way to order the nodes. Here we are using the alphabetical order, but with a real graph, there is no way to order the nodes, and so there is no way to ensure that we have a unique adjacency matrix for each graph. So when we change the order of the nodes, we will have a complete different adjacency matrix, which dramatically decrease the model accuracy if we base our input vector on this representation. Another may suggest to use the features vector only. This is a consistent representation indeed, but a graph dataset is a set of features along with a graph topology, and giving up the topology will lead to a big loss of relevant information that can top up the accuracy of the model, and we can't afford to give up on the topology if we want to have a very accurate model. So in order to extract information from the topology and not giving up on it, and use it along with the features matrix, we can think about performing some statistics over the graph topology, run some heuristics, and gather the results in a vector. This can indeed provide some insights about the topology and possibly improve the model accuracy. But the whole point about deep learning is to automatically perform features extractions. And that's why we need a CNN-like architecture for graph structured data. And these neural networks need to be able to perform directly on graph, exploiting both the topology and the provided features matrix, and also, by the way, make an automatical feature extraction. And there we are talking about a new subclass of neural networks, which are called the GNNs, and this answers the first questions, which is why we need a graph dedicated class of neural networks. Now we move to the second question, which is why this sudden interest. Like I said before, graphs are the most general data structures. Indeed, all the other regular data structures are special cases of graphs. An image can be seen as a grid, and thus it is a graph. An audio, it's a sequence of signals over time, so it can be represented as a graph also. And text is a bulk of words connected via grammar rules, so it can also be seen as a graph. Now, when you see the amazing achievements that deep learning achieved over these data types, and you see the large number of use cases where graphs can be used as representation model, you can't help but think about the possible breakthroughs if the use of neural networks could be extended to graph datasets. With graphs, we can model traffic networks, social networks, chemical molecules, citation graphs, financial transactions, and much more. And designing a powerful GNNs make it possible to better understand social interactions, to improve friend suggestions, to better detect communities in a network. And this application in particular can lead, for example, to forecasting a terrorist network expansion. If we can detect the communities in a network, we can forecast a terrorist network expansion, for example. GNNs make it possible also to derive new designs for new molecules, to simulate protein-protein interactions, predict a chemical property of a component, which cost a lot of money to be done in real labs. So how a GNN learn a vector representation of a node or of a graph? When we talked about representation learning in the CNN, I forgot to mention that the learning is done in an end-to-end fashion, which means that the representation learning and the inference of the last connected neural network is part of the same model, and the backpropagation of the loss function from the model output flows over the whole model. And the same thing goes for GNNs. For a given topology and a given set of features matrix, the first part of a GNN is in charge of learning a vector representation, which is called embedding, by the way. You will, if you search about graph deep learning, you will see a very large number of papers and articles talking about graph embedding and node embedding. So I was saying that the first part of a GNN is in charge of learning a vector representation or a node embedding, which is fed to a neural network that is part of the same GNN, the same model. And in the following slides, we will focus on the first part of the GNN, which is the part with the goal of learning a vector representation of a node. Actually, the researchers among the graph deep learning community have developed several methods to effectively exploit the graph topology in the learning process. But let's focus on the category of methods that borrows the locality features search and parameters sharing from CNNs. The idea with this category of methods is to build a node vector representation using its local neighborhood. So for this graph, for example, and if we choose the node A as a target, its representation is built using the representation of the neighbors. And the neighbors' representation is built from their neighbors also. This is where we see the locality principle. So for every node to have the representation vector of every node, we just need to be able to see the locality of this node target, to just see their immediately connected neighbors. And about the parameters sharing, for two targets like this, the weights in these boxes, all these boxes, the weights are the same in each level, and we will see that the boxes perform. We will see what the boxes perform soon enough. So for now, we will not discuss what these boxes do. But for now, what we need to know is that in each level, the weights and the parameter of these boxes are the same. And this is where we see the parameter sharing in this kind of methods. So you have already noticed that for every node, to get the representation vector of every node, the node must be selected as a target in order to build its final vector representation. And now, whatever these boxes do, we can already notice one difference and the challenge between an operation on a graph and the convolution on an image. Whereas an image is a regular data structures, like I said before, graphs are not, which means that when we look at a locality of a pixel, here, for example, when we look at the locality of the pixel G, we always have a fixed number of pixels, and an ordering is provided of the locality by using up, down, left, and right directions, which makes parameters sharing consistent and easy to reproduce. In the other hand, the size of a locality of a node may be completely different if we move from a node to another. Besides, the local neighbors can be taken in many possible orders. And keep in mind that the boxes are shared, and thus, if we want them to be defined as a graph operation, we must be able to deal. We must make them to be able to deal with such diversity. Let me recall that the boxes are used to gather information from the neighbors in order to build a targeted node's vector representation. So if we try to model what's happening in a graph computation like this one, we basically see that in a GNN for every node and for a given neighborhood, we need an aggregation function, which is the boxes that were presented earlier, and use the results to build a new representation for the target. So the most important thing about the aggregation function, which is performed by the boxes, we talked about in the previous slide. The most important thing about these boxes is to be invariant, which means they must be capable of treating a variable number of neighbors and in any order. The described recursivity defines the model layers. Every node has a representation at each layer, like we can see here. And the depth of the model is controlled by the number of updates we want to do before the final representation. And for the initial representation, so for the layer 0, we can take it as the vector representation taken from the features matrix, which is provided with the data set. And for the to explode the graph topology, the graph topology is exploited via the construction of the update scheme. So if we consider several graphs, every graph topology has its own update scheme, which means that in this way we are discovering the graph topology and we are using it in the learning process, which is one of the most important point about GNNs. Now let's give an example for an aggregation function. So let's open up this box. The mean operator is a suitable one. Why? Because no matter what the number of neighbors is, and the result stay the same. No matter the number of neighbors we take as input for the mean operator, the operation is still doable. So this is an operation which is independent from the number of terms as in the input. And whatever the order of the neighbors is, the results stay the same. So we can change the order of the neighbors as we want. The result stays always the same. And we can also use the max operator, the min operator, or even a recurrent unit cell. The most important thing is that the operation to be invariant to the number of invariant to the order we take the neighbors in, and doable whatever the number of neighbors is. And each use case gives us a different GNN architecture. So if we use the mean operator, the max operator, this what make the GNN architectures different from one another. And here in the here is the update operation. In order to update the vector representation, we can use this operation. So we can pass the aggregation through one layer, one fully connected layer, and use an activation function to as a non-linear function. So we can express the I'm still sharing the screen, right? Yes. Yes. So I was talking about the operation defined in the input and the output of this box. I was saying that in the input we have the aggregation function, which in this case we use the mean operator, and the output. In the output, we have an updated vector representation of the node A, and in the update we can use whatever activation function we want. It would be easier to handle the processing if we can deal with all the nodes at the same time. So not selecting a target node one by one and compute the graph and have at every step the computation graph and do the same job for every node. So what is better is to have an expression to deal with all the nodes at the same time. Using the mean operator as an aggregation function, we can express the whole process with a matrix product, which gives us this formula. So if we try to deal with all the nodes at the same time with in a matrix operation, we can reformulate the these operations that we defined earlier and put it in a matrix form and have this formula. And if we name this term as L, we can use this formula to define this two-layer GNN, where the first representation of the nodes, as we said, is the features matrix, which is given with the data set. And the second one, so the representation to give to the second layer, is the result of the first update. So as I said, we take the first representation, we perform the aggregation via the mean formula, and when we express it in a matrix form, this is the formula we get. We pass it through an activation function to have the update, and then we use the result as an input to the second layer, which is expressed in the same form of the formula in the previous slide. And the output, we use the softmax activation function if we are in the case of classification, for example. So you may have noticed that the depth of a GNN is very problematic. First, a deep GNN is very heavy to train. Indeed, you saw that the size of the updates scheme grows exponentially when the model gets deeper, and when the number of neighbors gets bigger also. And so do the memory conception and the memory consumption and the needed compute power. And there is also another GNN specific problem called over smoothing, and I'm not talking about overfitting, it's over smoothing. And this word refers to the point where the node's vector representation collapse to a single point, to a very similar representation. So all the vectors become similar, and thus it will be very difficult to make an accurate inference and distinguish between the nodes classes, for example, if we are in the case of a node classification problem. And this was an answer to the question of what's special about GNNs. So what tasks can be done with a GNN? A GNN can be used to do several tasks on a graph. For example, node prediction, where we give the model a graph with the proportion of labeled and unlabeled nodes. And the task is to complete the missed information in the graph by predicting a label for the unlabeled ones. And it can also be used for link prediction task. In a social network, for example, this can be the abstraction of a friend's suggestion problem, where the model will be able to predict if two persons have enough points in common that it would make sense if they were friends. GNNs give more accurate results on community detection or clustering over graph structured data, and also for graph regression problems, like I said earlier, for predicting a chemical property for molecule, for example. And since images and text can be seen as a graph, GNNs are also used in computer vision, NLP problems, They are also used in NAS, which is Neural Architecture Search, since the possible architectures are modeled using graphs. GNNs are used in point cloud for 3D meshes and 3D deep learning in general. And they are used to forecast traffic graphs. I recall recently I saw a DeepMind article where they reported the use of GNNs to improve the arrival time prediction on Google Maps. To conclude, let me recall that the particularity of graph structured data, the large use of graphs as an abstraction model in many fields are after the need of particular class of neural networks, which are GNNs. If we didn't have this particular class of data sets, we wouldn't have the need to define this new class of neural network. GNNs are models that make it possible to leverage a graph topology along with the dataset features, which is the most important added value that can a GNN bring when we compare it to a traditional neural network architecture. And GNNs can be used in several domains, as we saw in the previous slide. And this is because they deal with a general data structure, which is largely used as an abstraction model. We also saw that the depth in GNNs does not automatically mean improving the results, which is the case in CNNs, for example, because a deep GNN model can lead to a memory saturation or an over-smoothing problem that decreases the model accuracy. That's all. For the rest of the discussion, please feel free to speak in any language you want, English or Darja. The most important is that you benefit from the presentation.
Thank you very much, Abdurrahman. It was surely an interesting one, and you elaborated very well on every aspect. But I guess it was clear that no one asked questions. We don't have any questions for what you have talked about. I guess it was all clear. I really appreciate having you here, and it was a pleasure having you with us. Thank you for taking the time to do so.
Thank you very much.
Thank you. So, I guess we have arrived to the end of today's session talk. Thank you. I want to thank all the speakers that were here with us today. They took the time and efforts for their talks. Also, all the trainers for the workshops. And thank you for sticking with us till the end, and hope you enjoyed it. And also, I want to thank the whole team that have prepared and making this event so that we can share with you, give you insights about AI, and always keep you involved in the field. So take care, everyone, and have a nice evening. Thank you.